At this very moment, information is flowing through your device at impossible speeds, processed by billions of transistors, switching between two states millions of times per second. These classical bits, the foundation of every computer, smartphone, and digital device on Earth, can only exist in one of two definitive states: 0 or 1, on or off, true or false. This binary limitation has powered the entire digital revolution, yet it represents a fundamental barrier that has kept us locked within the boundaries of classical computation for decades. But what if I told you that scientists have discovered a way to break free from these constraints entirely, unlocking a realm where information can exist in multiple states simultaneously, where particles separated by vast distances can influence each other instantaneously, and where calculations that would take our most powerful supercomputers millions of years can be completed in mere moments? Welcome to the quantum world, where the impossible becomes inevitable and the rules of reality bend in ways that challenge everything we thought we knew about computation. If you're ready to dive into the mind-bending science that's about to revolutionize technology forever, hit that like button and let me know in the comments where you're watching from, because we're about to explore the most revolutionary breakthrough in computing since the invention of the transistor. The quantum bit, or qubit as scientists call it, represents the fundamental building block of a technological revolution that's happening right now in laboratories and tech companies around the world. Unlike the classical bits that power your current device, qubits harness the strange and counterintuitive properties of quantum mechanics to process information in ways that seem to violate the very fabric of reality. These microscopic marvels don't just switch between 0 and 1 like their classical counterparts. Instead, they exist in what physicists call superposition, a quantum state that allows them to be both 0 and 1 simultaneously until the moment they're observed. This concept sounds absolutely insane when you first encounter it, and honestly, it should. The idea that a single unit of information can exist in multiple states at once defies every intuition we've developed about how the world works. Yet this seemingly impossible phenomenon lies at the heart of quantum computing's extraordinary power. When classical computers process information, they must examine each possible solution to a problem one at a time, like searching through a massive library by checking every single book individually. Quantum computers, powered by qubits in superposition, can explore multiple solutions simultaneously, as if they could somehow read every book in the library at the exact same moment. The mathematical representation of qubits involves complex probability amplitudes that determine the likelihood of measuring the qubit in either the 0 or 1 state when observed. These aren't just abstract mathematical concepts floating in theoretical space. They represent real physical properties of actual particles and systems that scientists can manipulate and control with incredible precision. The probability amplitudes encode vastly more information than classical bits ever could, allowing quantum computers to perform calculations that push the boundaries of what we previously thought was computationally possible. But here's where quantum mechanics gets even more bizarre and powerful. Qubits don't just exist in superposition individually. They can also become entangled with each other, creating correlations that Albert Einstein himself called spooky action at a distance. When qubits become entangled, measuring the state of one qubit instantly determines the state of its entangled partner, regardless of how far apart they might be. This isn't just a curiosity for physicists to ponder in academic papers. Entanglement forms the backbone of quantum computing's computational advantage, allowing quantum systems to process information in ways that classical computers cannot efficiently replicate. The power of quantum entanglement becomes apparent when you consider how it scales. Two entangled qubits can exist in 4 possible combined states simultaneously. 3 qubits can represent 8 states at once. 4 qubits can handle 16 simultaneous states. The number of states grows exponentially with each additional qubit, creating computational power that doubles with every new quantum bit added to the system. This exponential scaling means that a quantum computer with just 50 qubits could theoretically explore more computational states than there are atoms in the observable universe. Yet building and maintaining these quantum systems presents challenges that push the limits of human engineering and scientific understanding. Qubits are incredibly fragile, existing in their quantum states for only microseconds or milliseconds before environmental interference destroys their delicate superposition. This process, called quantum decoherence, represents the greatest obstacle to building practical quantum computers. Any interaction with the surrounding environment, whether from air molecules, electromagnetic radiation, or even the tiniest vibrations, can collapse a qubit's superposition and destroy the quantum information it contains. The battle against decoherence has driven scientists to create some of the most extreme experimental conditions ever achieved on Earth. Many quantum computers operate at temperatures colder than outer space, just fractions of a degree above absolute zero, where atomic motion nearly stops entirely. These systems require sophisticated refrigeration equipment that can cost millions of dollars and consume enormous amounts of energy just to maintain the ultra-cold environment necessary for qubits to maintain. Despite these challenges, multiple their quantum states. Qubits have emerged, each with unique approaches to building Q advantages and limitations. Superconducting qubits, currently the most developed form of qubit technology, rely from on-circuits made materials that resistance when cooled to extremely conduct electricity without low temperatures. These circuits harness the Josephson effect, where quantum tunneling occurs across insulating barriers between superconducting materials, creating quantum states that can be precisely controlled using microwave pulses. Major technology companies like Google and IBM have invested billions of dollars in developing superconducting qubit systems, achieving remarkable milestones that demonstrate the practical potential of quantum computing. Google's latest quantum processor, the Willow chip, represents a watershed moment in quantum computing development. This system contains 105 superconducting qubits arranged in a sophisticated architecture that can detect and correct quantum errors faster than they accumulate, addressing one of the most fundamental challenges in building reliable quantum computers. The Willow chip's breakthrough in quantum error correction cannot be overstated in its importance. Previous quantum systems faced a paradox where adding more qubits typically increased the overall error rate, making larger systems less reliable than smaller ones. Willow demonstrates the opposite behavior, where error rates actually decrease as more qubits are added to the error correction system. This represents the first practical demonstration that quantum error correction can work in real-world systems, not just in theoretical models developed by physicists. This achievement marks the transition from what researchers call the noisy, intermediate-scale quantum era toward fault-tolerant quantum computing. Current quantum computers operate with significant error rates that limit their practical applications to specific problems where quantum advantage can overcome the noise. Fault-tolerant quantum computers, enabled by sophisticated error correction like that demonstrated in Willow, could run any quantum algorithm reliably, opening the door to revolutionary applications in cryptography, drug discovery, materials science, and artificial intelligence. Meanwhile, trapped ion quantum computers represent a completely different approach to harnessing quantum mechanics for computation. Instead of superconducting circuits, these systems use individual ions, charged atomic particles suspended in electromagnetic fields and manipulated using precisely controlled laser pulses. Trapped ion systems achieve some of the highest precision quantum operations ever demonstrated, with error rates so low that they approach the theoretical limits imposed by quantum mechanics itself. The isolation of trapped ions from environmental disturbances gives them exceptionally long coherence times compared to other qubit technologies. While superconducting qubits might maintain their quantum states for microseconds, trapped ions can preserve quantum information for seconds or even minutes. This extended coherence time provides a crucial complex advantage for running quantum algorithms that require many sequential operations without losing quantum information to decoherence. Companies like IonQ have aggressively pursued trapped ion technology, demonstrating the commercial viability of this approach through strategic acquisitions and technological development. IonQ's recent acquisition of Oxford Ionics for over $1 billion brings advanced ion trap-on-a-chip fabrication capabilities that could revolutionize the ability of trapped ion systems. This technology scale promises to miniaturize ion traps onto semiconductor chips, potentially enabling mass production of quantum computers using established semiconductor manufacturing processes. The competition between different qubit technologies reflects the broader race to achieve quantum supremacy and practical quantum advantage. Each approach offers unique benefits, Superconducting qubits can be fabricated using existing semiconductor techniques and integrated with classical electronics, while trapped ions provide unmatched precision and long coherence times. Other emerging technologies, including photonic qubits that use particles of light and topological qubits that harness exotic quantum states, represent additional pathways toward practical quantum computing. Amazon's recent introduction of the Ocelot quantum chip demonstrates yet another innovative approach to quantum error correction using CAT qubits. These systems exist in superpositions of coherent states that provide natural protection against certain types of quantum errors, potentially reducing error correction overhead by up to 90% compared to conventional approaches. This dramatic reduction in error correction costs could accelerate the timeline for practical quantum computing applications while addressing the enormous energy requirements of current quantum systems. The visualization of qubit states requires tools that can represent the complex mathematical relationships governing quantum superposition. Scientists use the Bloch sphere, an elegant three-dimensional representation that maps the infinite variety of possible qubit states onto the surface of a sphere. Classical bits could only exist at the north and south poles of this sphere, representing the definitive 0 and 1 states. Quantum bits can occupy any point on the sphere's surface, representing the vast range of superposition states available to quantum systems. Understanding the Bloch sphere becomes crucial for grasping how quantum operations work, as quantum gates correspond to rotations of the qubit state around different axes of the sphere. These rotations allow quantum computers to manipulate superposition and entanglement with mathematical precision, creating the complex quantum states necessary for quantum algorithms to achieve their computational advantages over classical methods. The journey from understanding individual qubits to building practical quantum computers requires mastering the delicate art of quantum control while battling the relentless forces of decoherence that constantly threaten to destroy quantum information. The battle against quantum decoherence has forced scientists to develop error correction techniques that seem almost as mysterious as the quantum phenomena they're designed to protect. Traditional computer error correction is straightforward. If a bit flips from 0 to 1 unexpectedly, you simply flip it back. But quantum error correction operates in a realm where directly observing quantum information destroys it, creating a paradox that seems impossible to solve. How do you detect and correct errors in quantum states without measuring them and thereby destroying the very information you're trying to protect? The solution involves one of the most elegant concepts in quantum physics, the quantum error correction code. These protocols work by spreading quantum information across multiple physical qubits in such a way that errors affecting individual qubits can be detected and corrected without ever directly measuring the protected quantum state. It's like having a secret message written in a code so sophisticated that even if parts of the message become corrupted, the original information can be perfectly reconstructed without anyone ever reading the actual secret. The mathematics behind quantum error correction codes reveals the true genius of this approach. By carefully entangling multiple physical qubits together, scientists create logical qubits that can survive the destruction of several individual components. The surface code, currently the most promising error correction architecture, requires hundreds or even thousands of physical qubits to create a single logical qubit. This massive overhead might seem wasteful, but it represents the price of admission to the fault-tolerant quantum computing era. Recent breakthroughs have demonstrated that this overhead isn't just theoretical. Google's Willow processor proved that quantum error correction can actually work in practice, showing that larger systems with more sophisticated error correction can achieve lower error rates than smaller systems. This counterintuitive result overturns decades of assumptions about quantum computing scalability and proves that the path to practical quantum computers is not just possible but inevitable. The implications of successful quantum error correction extend far beyond academic research laboratories. Fault-tolerant quantum computers could break the cryptographic systems that currently protect everything from banking transactions to government communications. The RSA encryption that secures your online purchases relies on the difficulty of factoring large numbers, a problem that would take classical computers longer than the age of the universe to solve for sufficiently large keys. A fault-tolerant quantum computer running Shor's algorithm could crack these codes in hours or days, rendering current cryptographic systems completely obsolete. This cryptographic vulnerability has sparked a global race to develop quantum-resistant encryption methods before practical quantum computers become widely available. Government agencies and technology companies are frantically working to implement post-quantum cryptography that can withstand attacks from both classical and quantum computers. The National Security Agency has issued urgent recommendations for organizations to begin transitioning to quantum-safe encryption algorithms, acknowledging that the quantum threat to cybersecurity is not a matter of if, but when. Yet the destructive potential of quantum computing represents only one side of a technological revolution that promises to transform virtually every field of human knowledge. Quantum computers excel at simulating quantum systems, a capability that could revolutionize our understanding of chemistry, materials science, and drug discovery. The complex quantum interactions that govern molecular behavior, catalytic reactions, and protein folding are precisely the types of problems where quantum computers could achieve exponential advantages over classical systems. The pharmaceutical industry spends decades and billions of dollars developing new medications through trial and error processes that quantum computers could potentially accelerate by orders of magnitude. Instead of synthesizing and testing thousands of potential drug candidates in laboratories, quantum simulations could explore molecular interactions in silico, identifying promising compounds before any physical experimentation begins. This capability could reduce the time and cost of drug development, while enabling the discovery of treatments for diseases that have resisted conventional approaches. Materials science presents another frontier where quantum computing could unlock revolutionary advances. The development of new materials with specific properties, from superconductors that work at room temperature to ultra-efficient solar cells, depends on understanding quantum mechanical interactions between atoms and electrons. Classical computers can model only the simplest material systems, forcing scientists to rely on experimental trial and error for most materials discovery. Quantum computers could simulate complex materials at the atomic level, accelerating the development of technologies ranging from better chips, the optimization batteries, to more efficient computer problems that plague modern logistics, finance, and artificial intelligence. Represent another domain where quantum computers could provide transformational advantages. Classical optimization algorithms must explore solution spaces sequentially, testing one possibility at a time until they find acceptable answers. Quantum algorithms can explore multiple solution paths simultaneously through superposition, potentially finding optimal solutions to problems that are intractable for classical computers. Financial portfolio optimization, traffic routing in smart cities, and resource allocation in supply chains all involve combinatorial optimization problems that grow exponentially more difficult as their size increases. A classical computer might need thousands of years to find the truly optimal solution to a complex scheduling problem, while a quantum computer could potentially solve the same problem in minutes or hours. This quantum advantage could unlock efficiencies in global commerce and infrastructure that translate to trillions of dollars in economic value. The integration of quantum computing with artificial intelligence promises to create hybrid systems that combine the pattern recognition capabilities of neural networks with the computational power of quantum processors. Machine learning algorithms require enormous amounts of computational resources to train on large data sets, and quantum computers could potentially accelerate this training process while enabling entirely new types of quantum machine learning algorithms that have no classical analogs. Quantum neural networks could process information in superposition states, exploring multiple learning pathways simultaneously rather than the sequential gradient descent methods used by classical systems. These quantum-enhanced artificial intelligence systems might solve problems that are fundamentally intractable for classical AI, from predicting protein structures to optimizing complex engineering designs that require exploring vast solution spaces. The timeline for these revolutionary applications depends critically on continued advances in qubit quality, error correction, and system scaling. Current quantum computers operate with dozens to hundreds of qubits, but practical applications will likely require systems with millions of high-quality qubits. The engineering challenges involved in scaling quantum systems to this size are immense, requiring breakthroughs in quantum control, error correction overhead, and the physical infrastructure needed to maintain quantum coherence across increasingly large systems. Manufacturing quantum computers at scale presents unique challenges that differ fundamentally from classical semiconductor production. The extreme environmental requirements for maintaining quantum coherence, the precision needed for quantum control systems, and the integration of quantum processors with classical electronics all require new manufacturing techniques and quality control processes. Companies are investing billions of dollars in developing quantum fabrication capabilities, but the transition from laboratory prototypes to commercial quantum systems remains one of the greatest technical challenges of our time. The software ecosystem surrounding quantum computing is evolving rapidly as researchers develop programming languages, algorithms, and development tools specifically designed for quantum systems. Writing quantum algorithms requires fundamentally different approaches from classical programming, as developers must think in terms of quantum gates, superposition states, and entanglement rather than the logical operations familiar from classical computing. Quantum programming languages like Qiskit, Cirq, and QNumberSign are enabling a new generation of quantum software developers to explore the computational possibilities of quantum systems. The race to achieve practical quantum advantage has created an ecosystem of competition and collaboration between technology giants, startups, academic institutions, and government research programs. Each player brings unique strengths to the quantum computing landscape, from IBM's long history in quantum research to Google's engineering expertise in building large-scale systems. Startups are exploring novel approaches to quantum hardware and software, while academic researchers continue pushing the fundamental science that underlies all quantum technologies. Government investment in quantum research has accelerated dramatically as nations recognize the strategic importance of quantum technologies for both economic competitiveness and national security. The United States has launched the National Quantum Initiative. China has invested tens of billions of dollars in quantum research, and the European Union has created the Quantum Flagship Program to coordinate quantum research across member countries. These massive public investments reflect the widespread recognition that quantum computing represents a technological inflection point comparable to the development of classical computers or the Internet. The global nature of quantum research has created both opportunities for international collaboration and concerns about technological competition. Quantum computing breakthroughs could provide significant advantages in areas ranging from drug discovery to cryptography, creating incentives for countries to protect their quantum research while also benefiting from international scientific cooperation. The balance between openness and security in quantum research will likely shape the development of quantum technologies for decades to come. As we stand on the threshold of the quantum computing era, the implications of this technology extend far beyond the technical specifications of qubits and quantum gates. We are witnessing the emergence of a computational paradigm that could reshape virtually every aspect of modern society, from the security of our digital infrastructure to the discovery of new medicines and materials. The quantum revolution isn't happening in some distant future laboratory. It's unfolding right now in facilities around the world where scientists are manipulating individual atoms with laser precision and cooling superconducting circuits to temperatures that make the coldest regions of space seem tropical. These quantum systems operate under conditions so extreme they push the boundaries of what's physically possible on Earth. Yet they're producing results that could transform every aspect of human civilization. Consider the sheer audacity of what quantum engineers are attempting to achieve. They're trying to harness particles that exist in multiple states simultaneously, control them with unprecedented precision, and maintain their quantum properties long enough to perform useful calculations. It's like trying to conduct a symphony orchestra where every musician is invisible, can play multiple instruments at once, and will disappear entirely if you listen too carefully to their performance. The technical challenges involved would have seemed like pure science fiction just decades ago. The race to build practical quantum computers has created an entirely new category of extreme engineering. Dilution refrigerators that cool quantum processors to temperatures approaching absolute zero consume enormous amounts of energy while maintaining conditions millions of times colder than the cosmic microwave background radiation fills the universe. These systems require such precise environmental control that a truck driving past the laboratory building could potentially introduce enough vibration to disrupt quantum calculations. Yet despite these seemingly impossible requirements, quantum computers are already demonstrating capabilities that hint at their revolutionary potential. IBM's quantum processors available through cloud computing platforms allow researchers worldwide to run quantum algorithms on real hardware, while Google's quantum supremacy demonstration proved that quantum systems can solve specific problems exponentially faster than the most powerful classical supercomputers ever built. These early achievements represent just the first glimpses of quantum computing's transformational power. The software running on these quantum systems operates according to principles that would confuse even experienced classical programmers. Quantum algorithms don't execute instructions sequentially like traditional software. Instead, they manipulate probability amplitudes across multiple quantum states simultaneously, creating interference patterns that amplify correct answers while canceling out incorrect ones. Writing quantum code requires thinking in terms of quantum gates, superposition phases, and entanglement topologies rather than the familiar logic, gates, and memory addresses of classical computing. This fundamental difference in quantum programming has spawned entirely new computer science disciplines focused on quantum algorithm design and quantum software optimization. Researchers are discovering that quantum systems excel at problems involving periodic functions, optimization landscapes, and simulation of quantum mechanical systems, while struggling with tasks that classical computers handle easily. The art of quantum programming lies in identifying problems where quantum mechanics provides genuine computational advantages rather than simply porting classical algorithms to quantum hardware. The economic implications of quantum computing breakthroughs extend far beyond the technology sector itself. Industries that rely heavily on computational optimization, from logistics companies managing global supply chains to financial institutions pricing complex derivatives, could see their operational efficiency transformed by quantum algorithms. The ability to solve previously intractable optimization problems could unlock trillions of dollars in economic value while enabling entirely new business models based on quantum-enhanced capabilities. Financial markets represent one of the most immediate applications for quantum computing advantages. Portfolio optimization, risk analysis, and algorithmic trading all involve complex mathematical problems that could benefit enormously from quantum acceleration. Investment firms are already experimenting with quantum algorithms for fraud detection, high-frequency trading optimization, and Monte Carlo simulations that model market behavior under various economic scenarios. The competitive advantages available to firms that successfully deploy quantum computing could reshape global financial markets. The pharmaceutical industry faces computational challenges perfectly suited to quantum solutions. Drug discovery currently requires decades of research and billions of dollars in development costs, largely because classical computers cannot efficiently simulate the quantum mechanical interactions that govern molecular behavior. Quantum computers could potentially model protein folding, enzyme catalysis, and drug-target interactions with unprecedented accuracy, accelerating the development of new medications while reducing costs and improving success rates. Climate science and environmental modeling represent another domain where quantum computing could provide crucial advantages. Understanding complex climate systems requires processing vast amounts of data while modeling intricate feedback loops between atmospheric, oceanic, and terrestrial systems. Quantum algorithms could potentially improve weather prediction accuracy, optimize renewable energy distribution systems, and accelerate the development of carbon capture technologies needed to address climate change. The intersection of quantum computing with artificial intelligence promises to create hybrid systems that combine quantum parallelism with machine learning pattern recognition. Quantum neural networks could process training data in superposition states, exploring multiple learning pathways simultaneously rather than the sequential optimization methods used by classical AI systems. These quantum-enhanced artificial intelligence systems might solve problems that remain intractable for even the most advanced classical neural networks. Machine learning applications in quantum systems face unique challenges that don't exist in classical computing environments. Quantum states cannot be copied directly due to fundamental quantum mechanical principles, making traditional machine learning techniques like backpropagation difficult to implement on quantum hardware. Researchers are developing entirely new approaches to quantum machine learning that work within these quantum constraints while leveraging quantum parallelism for computational advantages. The security implications of quantum computing advancement have created a sense of urgency throughout the cybersecurity industry. Current encryption methods rely on mathematical problems that classical computers cannot solve efficiently, but quantum computers running Shor's algorithm could break these systems with relative ease. This quantum threat has sparked a global transition to post-quantum cryptography designed to resist attacks from both classical and quantum computers. The timeline for this cryptographic transition remains uncertain, but the consequences of being unprepared could be catastrophic. Organizations that fail to implement quantum-resistant encryption before practical quantum computers become available could find their sensitive data completely exposed to adversaries with quantum capabilities. Government agencies worldwide are mandating transitions to quantum-safe encryption algorithms, acknowledging that the quantum threat represents an existential challenge to digital security. Paradoxically, quantum mechanics also provides the foundation for unbreakable quantum cryptography systems. Quantum key distribution protocols leverage the fundamental properties of quantum measurement to detect eavesdropping attempts with absolute certainty. Any attempt to intercept quantum encrypted communications necessarily disturbs the quantum states carrying the encrypted information, alerting legitimate users to the security breach. These quantum communication networks could provide perfect security for critical infrastructure and sensitive communications. The development of quantum internet infrastructure represents one of the most ambitious technological projects currently underway. Quantum networks require specialized hardware to generate, transmit, and detect individual photons carrying quantum information across fiber optic cables and satellite links. These systems must maintain quantum coherence across vast distances while providing the reliability and scalability needed for practical communication networks. Satellite-based quantum communication systems have already demonstrated the feasibility of quantum key distribution across continental distances. China's quantum communication satellite successfully transmitted quantum encrypted messages between ground stations thousands of kilometers apart, proving that quantum internet infrastructure is technically achievable. These demonstrations represent the first steps toward a global quantum communication network that could revolutionize secure communications. The manufacturing challenges involved in scaling quantum systems to industrial production levels require entirely new approaches to precision engineering and quality control. Quantum computers demand fabrication tolerances measured in atomic dimensions, environmental stability that exceeds the requirements of the most sensitive scientific instruments, and integration of quantum processors with classical control electronics. The semiconductor industry is adapting its manufacturing capabilities to meet these quantum requirements, but the transition involves fundamental changes to established production processes. Quality control in quantum manufacturing faces unique challenges that don't exist in classical electronics production. Testing quantum systems requires sophisticated measurement equipment that can characterize quantum states without destroying them, while statistical analysis must account for the probabilistic nature of quantum measurements. Manufacturing defects that would be barely noticeable in classical systems can completely destroy quantum coherence, requiring unprecedented attention to detail throughout the production process. The global quantum computing ecosystem has created new forms of international collaboration and competition that blur traditional boundaries between academic research and commercial development. Universities, national laboratories, and technology companies are forming partnerships that combine fundamental research with practical engineering development. These collaborations are accelerating quantum breakthroughs while creating complex intellectual property landscapes that span multiple countries and institutions. Talent development in quantum computing requires educational programs that bridge quantum physics, computer science, and engineering disciplines. Universities are creating quantum information science programs that train students in the interdisciplinary skills needed to advance quantum technologies. The shortage of qualified quantum engineers and researchers has become a limiting factor in quantum development, with companies competing aggressively to recruit talent from academic programs and competing organizations. The quantum computing industry has attracted massive venture capital investment as investors recognize the transformational potential of quantum technologies. Startup companies are exploring novel approaches to quantum hardware, software, and applications, while established technology giants invest billions of dollars in quantum research and development. This investment ecosystem is accelerating quantum innovation while creating competitive pressures that drive rapid technological advancement. Standards development for quantum computing involves international organizations working to establish common protocols for quantum hardware interfaces, software development tools, and quantum communication networks. These standards efforts face unique challenges because quantum technologies are still evolving rapidly, making it difficult to establish stable specifications that won't become obsolete as the technology advances. The balance between encouraging innovation and providing industry stability requires careful coordination among stakeholders worldwide. The quantum workforce of the future will require skills that span multiple scientific and engineering disciplines, from quantum mechanics and linear algebra to computer architecture and software development. Educational institutions are redesigning curricula to prepare students for careers in quantum technologies, while industry training programs help existing engineers transition into quantum roles. The success of the quantum revolution depends critically on developing human capital with the diverse skills needed to advance quantum technologies. As quantum computers transition from laboratory curiosities to practical tools, the integration of quantum systems with existing computing infrastructure presents enormous technical challenges. Hybrid quantum classical algorithms that leverage the strengths of both computational paradigms require sophisticated software architectures that can coordinate between fundamentally different types of processors. These hybrid systems represent path to near the most likely term quantum advantage in practical applications. The quantum computing revolution is creating ripple effects that extend far beyond the technology itself, influencing everything from international relations and economic competitiveness to scientific research methodologies and educational priorities. We are witnessing the emergence of a new technological paradigm that promises to reshape human civilization in ways we can barely begin to imagine. The emergence of quantum computing represents more than just another technological advancement. It signals a fundamental shift in how we approach the most challenging problems facing humanity, from modeling the behavior of exotic materials to optimizing the logistics networks that keep global commerce flowing. Yet the path from today's experimental quantum systems to tomorrow's revolutionary applications remains filled with obstacles that test the limits of human engineering ingenuity. Consider the delicate dance required to maintain quantum coherence in systems containing hundreds of qubits. Each additional quantum bit introduces new sources of potential interference, creating exponentially more complex interactions that must be controlled with atomic-level precision. The electromagnetic fields used to manipulate qubits must be calibrated to tolerances that make the precision of atomic clocks seem crude by comparison. A stray electromagnetic pulse from a cell phone tower kilometers away could potentially disrupt quantum calculations running in a heavily shielded laboratory. This extreme sensitivity has forced quantum engineers to develop isolation techniques that push the boundaries of what's physically achievable. Quantum computers operate inside chambers that provide better vacuum conditions than interstellar space while maintaining magnetic field stability that exceeds the requirements of the most sensitive scientific instruments. The cryogenic systems that cool superconducting qubits consume more electricity than small towns, yet they must maintain temperature stability measured in microkelvin while eliminating mechanical vibrations smaller than the diameter of atomic nuclei. The quantum control systems that orchestrate these impossibly precise conditions represent marvels of engineering that the most complex machines ever built. Microwave pulse sequences must be timed with femtosecond accuracy while maintaining phase relationships across dozens of quantum channels simultaneously. Classical control computers generate real-time feedback loops that adjust quantum operations faster than the coherence time of the qubits themselves, creating closed-loop control systems that operate at the fundamental limits of quantum mechanics. Yet despite these extraordinary technical requirements, quantum systems are beginning to demonstrate practical applications that justify their complexity. Quantum chemistry simulations running on current hardware have already provided insights into molecular behavior that would be impossible to obtain through classical computation alone. These early results hint at the revolutionary potential of quantum computers to accelerate scientific discovery in fields ranging from materials science to pharmaceutical development. The pharmaceutical industry faces computational bottlenecks that quantum systems seem uniquely positioned to address. Drug molecules interact with biological targets through quantum mechanical processes that classical computers can only approximate crudely. The binding affinity between a potential medication and its target protein depends on quantum effects, including electron tunneling, wave function overlap, and quantum mechanical resonance phenomena that classical simulations struggle to capture accurately. Quantum computers could potentially model these molecular interactions with unprecedented fidelity, allowing pharmaceutical researchers to predict drug efficacy and side effects before synthesizing physical compounds. This capability could transform drug discovery from a process dominated by experimental trial and error into a computational science guided by quantum mechanical principles. The economic implications are staggering, as the ability to identify promising drug candidates through quantum simulation could reduce development timelines from decades to years while dramatically improving success rates. Materials science presents another domain where quantum simulation could unlock transformational breakthroughs. The electronic properties of materials emerge from quantum mechanical interactions between vast numbers of atoms and electrons, creating computational problems that scale exponentially with system size. Classical computers can model only the simplest materials accurately, forcing materials scientists to rely on empirical approaches and experimental intuition for most materials discovery efforts. Quantum computers could potentially simulate complex materials at the electronic level, revealing how atomic arrangements give rise to macroscopic properties like electrical conductivity, magnetic behavior, and mechanical strength. This capability could accelerate the development of revolutionary materials, including room-temperature superconductors that could transform energy transmission, ultra-efficient photovoltaic cells that could make solar energy economically dominant, and advanced battery chemistries that could enable practical electric aviation. The optimization problems that pervade modern industry represent another area where quantum algorithms could provide decisive advantages. Supply chain management, financial portfolio optimization, and resource allocation all involve combinatorial problems where the number of possible solutions grows exponentially with problem size. Classical optimization algorithms must explore these solution spaces sequentially, often settling for approximate solutions because finding optimal answers would require computational resources that don't exist. Quantum optimization algorithms leverage superposition to explore multiple solution paths simultaneously, potentially finding optimal solutions to problems that are intractable for classical computers. The traveling salesman problem, a classic example of combinatorial optimization, involves finding the shortest route that visits all cities in a given set. For small numbers of cities, classical computers can find optimal solutions easily. But as the number of cities increases, the problem becomes exponentially more difficult, eventually requiring more computational time than the age of the universe. Quantum computers running specialized algorithms could potentially solve these optimization problems efficiently, unlocking applications in logistics planning, financial risk management, and resource scheduling that could save trillions of dollars annually while improving efficiency across industries. Airlines entire could optimize flight schedules and crew assignments in real time, adapting to weather disruptions and passenger demand fluctuations with unprecedented agility. Manufacturing companies could optimize production schedules across global supply chains, minimizing waste while maximizing throughput. The integration of quantum computing with artificial intelligence promises to create hybrid systems that combine quantum parallelism with pattern recognition capabilities. Current machine learning algorithms require enormous computational resources to train neural networks on large datasets, often requiring weeks or months of processing time on specialized hardware. Quantum-enhanced machine learning could potentially accelerate this training process while enabling entirely new types of learning algorithms that have no classical analogs. Quantum neural networks could process training data in superposition states, exploring multiple learning pathways simultaneously rather than the sequential optimization methods used by classical systems. This quantum parallelism could enable artificial intelligence systems to discover patterns in data that remain hidden from classical machine learning approaches. The combination of quantum computation with advanced AI could accelerate breakthroughs in fields ranging from climate modeling to protein structure prediction. Financial markets represent one of the most immediate applications for quantum computing advantages, as trading algorithms and heavily risk management systems rely on optimization problems that could benefit from quantum acceleration. High-frequency trading firms already invest billions of dollars in computational infrastructure to gain microsecond advantages in market timing. Quantum algorithms could potentially provide even more dramatic improvements in trading efficiency while enabling new approaches to portfolio optimization and risk assessment. Monte Carlo simulations used in financial modeling involve sampling random variables to estimate complex probability distributions. These simulations require enormous computational resources for accurate results, often running for hours or days on powerful classical computers. Quantum algorithms could potentially achieve similar accuracy with exponentially fewer computational steps, enabling real-time risk assessment and decision-making that could transform financial markets. The cryptographic implications of quantum computing advancement have created a sense of urgency throughout the cybersecurity community that extends far beyond theoretical concerns. Current public key encryption systems rely on mathematical problems that quantum computers could solve efficiently, potentially rendering most digital security systems obsolete overnight. The RSA encryption that protects everything from online banking to government communications could be broken by quantum computers running Shor's algorithm. This quantum threat has sparked a global transition to post-quantum cryptography designed to resist attacks from both classical and quantum computers. The National Institute of Standards and Technology has standardized quantum-resistant encryption algorithms after years of evaluation. Organizations worldwide are racing and testing to implement these new cryptographic systems before practical quantum computers become widely available. The timeline for this cryptographic transition remains uncertain, but the stakes could not be higher. Financial institutions that fail to implement quantum-resistant encryption could find their customer data completely exposed to adversaries with quantum capabilities. Government agencies responsible for national security face similar vulnerabilities if they don't transition to quantum-safe systems before the quantum threat materializes. Paradoxically, quantum mechanics also provides the foundation for unbreakable communication security through quantum key distribution protocols. These systems leverage the fundamental properties of quantum measurement to detect eavesdropping attempts with absolute certainty. Any attempt to intercept quantum encrypted communications necessarily disturbs the quantum states carrying the information, alerting legitimate users to the security breach. Quantum communication networks using satellite links and fiber optic cables have already demonstrated the feasibility of quantum-secured communications across continental distances. China's quantum satellite program has achieved quantum key distribution between ground stations thousands of kilometers apart, proving that global quantum communication infrastructure is technically achievable. These systems could provide perfect security for critical infrastructure and sensitive communications. The development of quantum internet architecture represents one of the most ambitious engineering projects currently underway. Quantum networks require specialized hardware to generate, transmit, and detect individual photons carrying quantum information across vast distances while maintaining quantum coherence. These systems must provide the reliability and scalability needed for practical communication networks while operating at the fundamental limits of quantum mechanics. Quantum repeaters, analogous to classical signal amplifiers, face unique challenges because quantum information cannot be copied or amplified directly. Instead, quantum repeaters use quantum error correction and quantum teleportation protocols to extend the range of quantum communications. The engineering complexity of these systems rivals that of quantum computers themselves, requiring precise coordination between quantum memory elements, entanglement generation systems, and classical communication channels. The manufacturing challenges involved in scaling quantum systems to commercial production levels require entirely new approaches to precision engineering and quality control. Semiconductor fabrication facilities must adapt their processes to meet quantum requirements while maintaining the high-volume production capabilities needed for commercial viability. The tolerances required for quantum device fabrication exceed those of the most advanced classical semiconductors by several orders of magnitude. Quality assurance in quantum manufacturing faces the fundamental challenge that quantum states cannot be measured without destroying them. Testing quantum devices requires statistical methods that can characterize system performance without directly observing the quantum states themselves. Manufacturing defects that would be inconsequential in classical electronics can completely eliminate quantum coherence, requiring unprecedented attention to detail throughout the production process. The global quantum ecosystem has created new forms of competition and collaboration that transcend traditional industry boundaries. Technology companies, national laboratories, universities, and government agencies are forming partnerships that combine fundamental research with practical engineering development. These collaborations are accelerating quantum breakthroughs while creating complex intellectual property landscapes that span multiple countries and institutions. International competition in quantum technologies has intensified as nations recognize the strategic importance of quantum capabilities for both economic competitiveness and national security. The United States, China, and European Union have launched massive public investment programs in quantum research, while smaller nations are developing niche specializations in specific quantum technologies. This global competition is driving rapid advancement while creating concerns about technological sovereignty and supply chain security. Talent development in quantum computing has become a critical bottleneck limiting the pace of quantum advancement. The interdisciplinary nature of quantum technologies requires professionals with expertise spanning quantum physics, computer science, electrical engineering, and materials science. Universities are creating new degree programs in quantum information science, while companies compete aggressively to recruit qualified quantum engineers and researchers. The quantum workforce shortage extends beyond technical roles to include business development, intellectual property law, and regulatory compliance professionals who understand quantum technologies. This talent gap is creating opportunities for professionals willing to acquire quantum expertise while limiting the growth rate of quantum companies and research programs. Educational institutions and industry training programs are working to address this shortage, but developing quantum expertise requires years of specialized education and experience. Venture capital investment in quantum technologies has accelerated dramatically as investors recognize the transformational potential of quantum systems. Quantum startups are attracting billions of dollars in funding, while established technology companies acquire quantum expertise through strategic investments and acquisitions. This investment ecosystem is accelerating quantum innovation while creating competitive pressures that drive rapid technological advancement. The quantum investment landscape reflects the high-risk, high-reward nature of quantum technologies. Many quantum applications remain years or decades away from commercial viability, yet the potential returns from successful quantum breakthroughs could dwarf any previous technological revolution. Investors must balance the enormous potential of quantum technologies against the significant technical and market risks associated with emerging quantum companies. Standards development for quantum computing involves international organizations working to establish common protocols for quantum hardware interfaces, software development tools, and quantum communication networks. These standardization efforts face unique challenges because quantum technologies are evolving rapidly, making it difficult to establish stable specifications that won't become obsolete as technology advances. The balance between encouraging innovation and providing industry stability requires careful coordination among diverse stakeholders. Quantum software development tools are evolving rapidly as researchers create programming languages, compilers, and development environments specifically designed for quantum systems. These tools must bridge the gap between quantum mechanical principles and practical software development, while providing the abstraction layers needed for non-experts to utilize quantum capabilities. The emergence of cloud-based quantum computing platforms is democratizing access to quantum systems while accelerating software development. The integration of quantum systems with existing computing infrastructure presents complex challenges that require hybrid architectures capable of coordinating between fundamentally different types of processors. Classical computers excel at logical operations, data storage, and user interfaces, while quantum computers provide advantages for specific mathematical problems. Hybrid systems that leverage the strengths of both computational paradigms represent the most likely path to near-term quantum advantage. Quantum cloud computing platforms are making quantum resources accessible to researchers and developers worldwide, removing the barriers associated with building and maintaining quantum hardware. These platforms provide standardized interfaces that allow users to run quantum algorithms on different hardware architectures, while abstracting away the complexity of quantum system operation. The democratization of quantum access is accelerating innovation while creating new business models for quantum computing services. The quantum revolution extends beyond technological advancement to encompass fundamental changes in how we approach scientific research, economic optimization, and information security. We are witnessing the emergence of a computational paradigm that could reshape human civilization in ways that extend far beyond our current imagination. The quantum future isn't arriving in some distant tomorrow. It's being built right now in laboratories and companies around the world, one precisely controlled quantum state at a time. The quantum advantage that scientists have been chasing for decades is finally materializing in ways that should fundamentally terrify and inspire anyone who understands what's at stake. We're not talking about incremental improvements or marginal gains in computational efficiency. We're witnessing the emergence of computational capabilities that could render entire industries obsolete while simultaneously creating possibilities that stretch the boundaries of what we thought was achievable with any technology. The pharmaceutical giant Roche recently partnered with Cambridge Quantum Computing to tackle one of the most computationally intensive problems in modern medicine: modeling the behavior of complex protein interactions in real time. Classical supercomputers attempting this same calculation would require computational resources equivalent to the entire global internet running continuously for thousands of years. The quantum system produced preliminary results in under 6 hours. This isn't just faster computation. This represents a fundamental leap beyond what classical physics allows any traditional computer to achieve, regardless of how much money or energy you throw at the problem. But the implications stretch far beyond accelerating existing processes. Quantum computers are revealing solutions to problems we didn't even know were solvable. Consider the three-body problem that has plagued physicists since Newton's time. When three objects interact gravitationally, their motions become chaotic in ways that classical mathematics cannot predict with perfect accuracy. Quantum algorithms are beginning to find stable solutions to multi-body gravitational systems by exploring all possible orbital configurations simultaneously through superposition. This capability extends to modeling the behavior of financial markets, where thousands of interconnected variables create complexity that overwhelms traditional analysis methods. Goldman Sachs has quietly deployed quantum algorithms for portfolio risk assessment that can evaluate market scenarios classical computers would need centuries to explore. The quantum system identifies profitable trading opportunities by analyzing correlation patterns across global markets in ways that reveal hidden mathematical relationships invisible to conventional analysis. The energy industry faces optimization challenges that perfectly match quantum computing's unique strengths. Power grid management involves coordinating thousands of generators, transmission lines, and consumption centers in real time while accounting for weather patterns, equipment failures, and fluctuating demand. Classical optimization algorithms must make approximations that result in billions of dollars in wasted energy annually. Quantum optimization could potentially eliminate this waste while improving grid stability and reducing carbon emissions. IBM's quantum processors are already demonstrating practical advantages in logistics optimization that could transform global commerce. The problem of efficiently routing delivery trucks through urban environments involves exponentially complex calculations as the number of stops increases. Classical algorithms settle for approximate solutions because finding optimal routes would require computational resources that don't exist. Quantum routing algorithms can explore all possible delivery sequences simultaneously, finding solutions that reduce fuel consumption and delivery times while improving customer satisfaction. The aerospace industry presents another domain where quantum simulation could unlock revolutionary advances. Designing aircraft involves modeling complex fluid dynamics, structural mechanics, and thermodynamic interactions that push classical computers to their limits. Wind tunnel testing and prototype development consume years of time and billions of dollars because classical simulations cannot accurately predict how air flows around complex geometries under all flight conditions. Quantum fluid dynamics simulations could potentially model airflow with molecular-level accuracy, revealing optimal wing designs and engine configurations without physical testing. Boeing has invested heavily in quantum computing research specifically to accelerate aircraft design while reducing development costs. The ability to simulate complete flight envelopes computationally could enable aircraft designs that are impossible to validate through traditional engineering approaches. Weather prediction represents one of the most computationally demanding challenges in science, involving the integration of atmospheric data across multiple scales from molecular interactions to continental weather systems. Current weather models must make approximations that limit prediction accuracy beyond a few days because the computational requirements grow exponentially with forecast duration and resolution. Quantum atmospheric modeling could potentially extend accurate weather forecasts to weeks or months while providing the precision needed for agriculture, disaster preparedness, and renewable energy planning. The European Space Agency has initiated quantum weather modeling research that aims to predict climate patterns with unprecedented accuracy by simulating the quantum mechanical processes that drive atmospheric chemistry. These simulations could reveal how trace gases interact with solar radiation and cosmic particles to influence global climate systems. The ability to model climate change with quantum precision could guide policy decisions while identifying intervention strategies that classical climate models cannot evaluate. Artificial intelligence training represents another application where quantum acceleration could provide transformational advantages. Current neural networks require enormous amounts of computational resources and training data to achieve human-level performance in specific domains. The largest language models consume electricity equivalent to small cities while training on datasets that represent significant fractions of all human-generated text. Quantum machine learning algorithms could potentially achieve similar performance with exponentially less training data and computational resources. Quantum neural networks process information in superposition states, enabling learning algorithms that explore multiple optimization paths simultaneously. This quantum parallelism could accelerate AI development while enabling entirely new types of artificial intelligence that have no classical analogs. The intersection of quantum computing with biotechnology promises to revolutionize our understanding of living systems at the molecular level. DNA sequencing, protein folding, and cellular metabolism all involve quantum mechanical processes that classical computers can only approximate. Quantum biological simulations could reveal how quantum effects in photosynthesis, enzyme catalysis, and neural signaling contribute to the efficiency of biological systems. Researchers at MIT are using quantum computers to model the quantum coherence effects that occur in bird navigation systems. These biological quantum sensors enable migratory birds to detect magnetic fields with sensitivity that exceeds the best human-made instruments. Understanding these quantum biological mechanisms could lead to revolutionary sensor technologies and navigation systems that operate with unprecedented precision. The pharmaceutical applications of quantum biology extend beyond drug discovery to encompass personalized medicine based on individual quantum genetic signatures. Every person's DNA contains unique quantum mechanical properties that influence how they metabolize medications and respond to treatments. Quantum genetic analysis could enable precision medicine that accounts for quantum effects in cellular biochemistry, optimizing treatments for individual patients based on their molecular quantum signatures. Quantum sensing technologies are already demonstrating capabilities that surpass classical measurement systems by orders of magnitude. Quantum gravimeters can detect gravitational anomalies so subtle that they reveal underground oil deposits, mineral veins, and archaeological structures that traditional surveys miss completely. These quantum sensors operate by measuring how gravitational fields affect the quantum states of trapped atoms, achieving sensitivity levels that approach fundamental physical limits. The defense applications of quantum sensing are creating entirely new categories of military technology. Quantum radar systems can detect stealth aircraft by measuring quantum entanglement disruptions caused by objects moving through quantum fields. These systems remain effective even when classical radar signals are jammed or absorbed by stealth coatings. Quantum sonar could provide similar advantages for submarine detection by measuring quantum field perturbations in ocean environments. Navigation systems based on quantum sensing could provide GPS-level accuracy without relying on satellite signals. Quantum inertial guidance systems measure acceleration and rotation by monitoring how motion affects quantum states, providing navigation capabilities that work underwater, underground, or in space environments where GPS signals are unavailable. These quantum navigation systems could enable autonomous vehicles that operate reliably in GPS-denied environments. The manufacturing industry faces quality control challenges that quantum sensing could revolutionize. Detecting microscopic defects in semiconductor wafers, aircraft components, and medical devices requires measurement precision that pushes classical sensors to their limits. Quantum sensors can detect structural flaws, chemical contamination, and stress concentrations with atomic-level resolution, enabling quality control processes that ensure product reliability while reducing manufacturing waste. Medical imaging represents another domain where quantum sensors could provide transformational improvements. Magnetic resonance imaging systems enhanced with quantum sensors could detect diseases at cellular levels while using lower magnetic field strengths that eliminate safety concerns. Quantum-enhanced MRI could reveal brain activity patterns, cardiovascular function, and tumor growth with resolution and sensitivity that classical medical imaging cannot achieve. The agricultural applications of quantum sensing could optimize crop yields while reducing environmental impact. Quantum soil sensors can detect nutrient levels, moisture content, and microbial activity with precision that enables targeted fertilizer application and irrigation scheduling. These sensors could guide precision agriculture systems that maximize productivity while minimizing water usage and chemical runoff. Environmental monitoring using quantum sensors could detect pollution, climate changes, and ecosystem health with sensitivity that enables early intervention before environmental damage becomes irreversible. Quantum air quality sensors can identify trace gases and particulates at concentrations far below the detection limits of classical instruments. This capability could guide environmental policy decisions while providing early warning systems for industrial accidents and natural disasters. The quantum internet represents the next evolution of global communications infrastructure, promising security guarantees that no classical system can provide. Quantum key distribution networks already connect major cities in China, Europe, and North America, demonstrating that quantum-secured communications are technically feasible at national scales. These networks provide perfect security by leveraging quantum mechanical principles that make eavesdropping physically impossible. Satellite-based quantum communication systems could extend quantum internet coverage globally while providing secure communications for spacecraft, military operations, and remote research facilities. The European Space Agency's Quantum Satellite Program aims to create a global quantum communication network that connects ground stations across all continents. This infrastructure could provide unhackable communications for critical applications while enabling new forms of quantum-enhanced services. Quantum computing applications in space exploration could revolutionize how we navigate and explore the solar system. Mission planning for interplanetary spacecraft involves optimization problems that grow exponentially complex as mission duration and complexity increase. Quantum trajectory optimization could find fuel-efficient paths through the solar system while accounting for gravitational assists, orbital mechanics, and equipment constraints that classical optimization cannot handle efficiently. The search for extraterrestrial intelligence could benefit from quantum signal processing algorithms that can detect patterns in cosmic radiation that classical analysis methods miss. Quantum pattern recognition systems could identify artificial signals buried in cosmic background noise while distinguishing between natural astronomical phenomena and potential technological signatures from alien civilizations. Mining operations on asteroids and other celestial bodies present logistical challenges that quantum optimization could address. Coordinating mining equipment, processing facilities, and transportation systems across interplanetary distances requires planning capabilities that exceed classical computational limits. Quantum logistics algorithms could optimize space-based resource extraction while minimizing costs and risks associated with operating in hostile environments. The intersection of quantum computing with renewable energy systems could accelerate the transition to sustainable energy infrastructure. Solar panel efficiency depends on quantum mechanical processes that convert photons into electrical current. Quantum simulations of photovoltaic materials could reveal new semiconductor compositions and nanostructures that achieve higher conversion efficiencies while reducing manufacturing costs. Wind farm optimization involves complex calculations that account for wind patterns, turbine interactions, and electrical grid integration. Quantum optimization algorithms could maximize energy production from wind farms while minimizing environmental impact and maintenance costs. These systems could adapt wind turbine operations in real time based on weather forecasts and electrical demand patterns. Energy storage systems based on quantum mechanical principles could store and release electricity with efficiencies that approach theoretical limits. Quantum battery technologies leverage quantum coherence to store energy in quantum states that remain stable for extended periods without degradation. These systems could enable renewable energy grids that provide consistent power output despite variable generation from solar and wind sources. The quantum revolution in computing, sensing, and communications represents more than technological advancement. It signifies humanity's transition into a new era where we can harness the fundamental properties of reality itself to solve problems that have limited human civilization for millennia. We are learning to manipulate the quantum substrate that underlies all physical phenomena, gaining capabilities that our ancestors would have considered indistinguishable from magic. Yet this quantum transformation also creates new forms of vulnerability and risk that we're only beginning to understand. The same quantum computers that could revolutionize medicine and materials science could also break the encryption systems that protect modern civilization's digital infrastructure. The quantum sensors that could detect diseases and environmental threats could also enable surveillance capabilities that eliminate privacy entirely. The quantum future demands that we carefully balance the enormous benefits of quantum technologies against their potential for misuse or unintended consequences. The choices we make today about how to develop, deploy, and regulate quantum systems will determine whether this quantum revolution enhances human welfare or creates new categories of risk that threaten the foundations of democratic society. The quantum age is not approaching gradually. It's arriving with exponential acceleration as breakthrough after breakthrough compounds to create capabilities that seemed impossible just years ago. The organizations, nations, and individuals who understand and adapt to this quantum transformation will shape the future of human civilization. Those who ignore or misunderstand the quantum revolution may find themselves as obsolete as mechanical calculators in the age of classical computers. The quantum domain operates according to principles that challenge our most basic intuitions about reality, yet mastering these principles provides access to computational, sensing, and communication capabilities that transcend the limitations that have constrained human achievement throughout history. We stand at the threshold of the quantum age, equipped with technologies that could solve humanity's greatest challenges while opening doorways to possibilities we cannot yet imagine. The quantum revolution will touch every aspect of human experience, From the medicines that heal us to the materials that shelter us, from the algorithms that guide our decisions to the sensors that protect our environment. Understanding quantum technologies isn't just an academic curiosity or a professional necessity. It's becoming essential knowledge for anyone who wants to comprehend the world that's rapidly emerging around us. The quantum transformation of human civilization has already begun. The only question that remains is whether we'll shape this transformation consciously and deliberately, or whether we'll be swept along by forces we don't understand toward futures we didn't choose. The quantum age offers unprecedented power to those wise enough to wield it responsibly, and catastrophic risks to those who ignore its implications. The future belongs to those who can think quantum. The quantum mechanics operating inside these miraculous systems follow rules so bizarre that even Albert Einstein spent his final years trying to prove they couldn't possibly be true. He called quantum entanglement spooky action at a distance because he refused to accept that particles could instantaneously influence each other across cosmic distances. Yet Einstein was wrong about quantum mechanics, and his discomfort with quantum reality inadvertently highlighted the most powerful computational resource in the universe. When quantum particles become entangled, they form connections that transcend space and time in ways that make science fiction look conservative. Measure the spin of one entangled electron, and its partner electron on the opposite side of the galaxy instantly snaps into the corresponding state. This isn't communication traveling at light speed. This is instantaneous correlation that occurs faster than light could possibly travel between the particles. The implications for information processing are staggering. Classical computers must send signals between components at speeds limited by the physics of electrical transmission. Even light-speed signals create bottlenecks when processors attempt to coordinate operations across large systems. Quantum computers bypass these limitations entirely by utilizing entanglement to create instantaneous correlations between qubits, regardless of their physical separation. This enables quantum processors to achieve coordination that would be impossible in any classical system. The engineering challenges of maintaining entanglement across multiple qubits push quantum systems into regimes where the boundary between physics and engineering dissolves completely. Creating entangled states requires pulse sequences timed with precision that makes atomic clocks seem crude. Maintaining these entangled networks demands environmental control that exceeds the stability of the most sensitive scientific instruments ever constructed. Yet when these conditions are achieved, quantum computers demonstrate capabilities that seem to violate fundamental assumptions about computation itself. Google's Sycamore processor famously completed a calculation in 200 seconds that would require the world's most powerful classical supercomputer 10,000 years to finish. This quantum supremacy demonstration proved that quantum computers can solve certain problems exponentially faster than any classical system, regardless of future improvements in traditional computing hardware. The mathematical foundations underlying quantum computation reveal why these systems can achieve such extraordinary performance advantages. Classical bits exist in definite states that can be represented by real numbers 0 and 1. Quantum bits exist in complex probability spaces described by wave functions that can encode vastly more information than classical states. The probability amplitudes of qubits can interfere with each other constructively or destructively, creating computational pathways that have no classical analog. This quantum interference enables algorithms that solve problems by amplifying correct answers while canceling incorrect ones. Grover's search algorithm can find specific items in unsorted databases quadratically faster than any classical search method by using quantum interference to boost the probability of measuring the correct answer. Shor's factoring algorithm achieves exponential speedups by exploiting quantum periodicity detection that reveals the mathematical structure hidden within large composite numbers. The cryptographic implications of Shor's algorithm have created a security crisis that extends far beyond academic computer science. The RSA encryption protecting online banking, government communications, and corporate data relies on the difficulty of factoring large numbers into their prime components. Classical computers would need longer than the age of the universe to factor the numbers used in modern encryption keys. Quantum computers running Shor's algorithm could break these same encryption systems in hours. This quantum threat has triggered a global race to develop post-quantum cryptography that can resist attacks from both classical and quantum computers. The National Security Agency has issued emergency guidelines urging immediate transitions to quantum-resistant encryption algorithms. Financial institutions are investing billions of dollars in cryptographic upgrades, while government agencies classify quantum computing research as a national security priority. The timeline for this cryptographic vulnerability remains uncertain, but the consequences of being unprepared could be catastrophic. Organizations that fail to implement quantum-resistant encryption before large-scale quantum computers become available could find decades of sensitive data completely exposed to adversaries with quantum capabilities. The quantum threat represents an existential challenge to digital security that demands immediate attention despite the technical complexity of quantum-safe cryptographic systems. Paradoxically, quantum mechanics also provides the foundation for perfect cryptographic security through quantum key distribution protocols. These systems leverage the fundamental measurement properties of quantum states to detect eavesdropping with absolute certainty. Any attempt to intercept quantum encrypted communications necessarily disturbs the quantum states carrying the information, immediately alerting legitimate users to security breaches. Quantum communication networks utilizing satellite links and fiber optic infrastructure have already demonstrated intercontinental quantum key distribution with security guarantees that no classical system can provide. China's quantum satellites successfully transmitted quantum-encrypted messages between ground stations separated by thousands of kilometers, proving that global quantum communication infrastructure is technically achievable with current technology. The development of quantum internet architecture represents one of the most ambitious engineering projects in human history. Quantum networks require specialized hardware capable of generating, transmitting, and detecting individual photons while preserving their quantum properties across vast distances. These systems must maintain quantum coherence through atmospheric turbulence, fiber optic imperfections, and electromagnetic interference, while providing the reliability needed for practical communications infrastructure. Quantum repeaters, the quantum equivalent of classical signal amplifiers, face unique challenges because quantum information cannot be copied or amplified directly without destroying its quantum properties. Instead, quantum repeaters use quantum error correction and teleportation protocols to extend communication range while preserving quantum security. The engineering complexity of these systems rivals that of quantum computers themselves, requiring precise coordination between quantum memory elements, entanglement generation systems, and classical control networks. The quantum sensing revolution occurring alongside quantum computing advances promises measurement capabilities that surpass classical instruments by orders of magnitude. Quantum sensors leverage the extreme sensitivity of quantum states to external disturbances, achieving precision that approaches fundamental physical limits imposed by quantum mechanics itself. These sensors can detect gravitational waves, magnetic fields, and acceleration changes with sensitivity levels that reveal previously hidden phenomena. Atomic gravimeters using quantum interferometry can detect gravitational anomalies so subtle that they reveal underground geological structures, mineral deposits, and archaeological sites that traditional surveys cannot locate. These quantum sensors measure how gravitational fields affect the wave functions of trapped atoms, achieving gravitational sensitivity that enables exploration applications ranging from oil prospecting to earthquake prediction. Quantum magnetometers can detect magnetic field variations smaller than those produced by a human heartbeat at distances of several meters. Medical applications of quantum magnetic sensing could revolutionize diagnostics by detecting magnetic signatures of cellular activity, blood flow patterns, and neural function with unprecedented resolution. These sensors could identify diseases at molecular levels while using magnetic fields too weak to pose any safety concerns. The navigation applications of quantum sensing could provide GPS-level positioning accuracy without relying on satellite signals. Quantum inertial guidance systems measure acceleration and rotation by monitoring how motion affects quantum states, enabling navigation capabilities that work reliably underwater, underground, or in space environments where satellite communications are unavailable. Military and civilian applications of quantum navigation could transform transportation systems while providing backup capabilities for GPS-dependent infrastructure. Quantum timing networks could synchronize global telecommunications, financial trading systems, and scientific instruments with precision that enables entirely new categories of coordinated operations. Quantum clocks achieve timekeeping accuracy that exceeds current atomic clocks by several orders of magnitude, maintaining synchronization across global networks with precision measured in attoseconds rather than nanoseconds. The manufacturing applications of quantum sensors promise quality control capabilities that could eliminate defects while reducing waste throughout industrial production processes. Quantum strain sensors can detect mechanical stress, temperature variations, and material composition changes with atomic level resolution. These sensors could monitor manufacturing processes in real time, identifying potential failures before they occur while optimizing production parameters for maximum efficiency. Environmental monitoring using quantum sensors could detect pollution, climate changes, and ecosystem health indicators with sensitivity that enables intervention before environmental damage becomes irreversible. Quantum chemical sensors can identify trace gases and pollutants at concentrations far below the detection limits of classical analytical instruments. This capability could guide environmental policy while providing early warning systems for industrial accidents and natural disasters. The agricultural applications of quantum sensing could optimize crop yields while minimizing environmental impact through precision farming techniques guided by quantum soil analysis and plant health monitoring. Quantum sensors could detect nutrient levels, moisture content, and pest activity with precision that enables targeted interventions using minimal chemical inputs while maximizing agricultural productivity. Space exploration missions could benefit enormously from quantum sensing technologies that enable precise navigation, resource detection, and scientific measurement capabilities in extreme environments. Quantum sensors could detect gravitational anomalies that reveal the internal structure of planets and asteroids while providing navigation references that enable precise maneuvering around celestial bodies. The intersection of quantum computing with artificial intelligence promises hybrid systems that combine quantum parallelism with machine learning pattern recognition capabilities. Current neural network training requires enormous computational resources and months of processing time on specialized hardware. Quantum-enhanced machine learning could potentially accelerate training processes while enabling AI systems that discover patterns invisible to classical algorithms. Quantum neural networks could process training data in superposition states, exploring multiple learning pathways simultaneously rather than the sequential optimization methods required by classical systems. This quantum parallelism could enable artificial intelligence breakthroughs that solve problems remaining intractable for even the most advanced classical neural networks. The combination of quantum computation with advanced AI could accelerate scientific discovery across disciplines ranging from materials science to pharmaceutical development. Machine learning applications in quantum systems face unique constraints that don't exist in classical computing environments. Quantum states cannot be copied directly due to fundamental quantum mechanical principles, making traditional neural network techniques like backpropagation challenging to implement on quantum hardware. Researchers are developing entirely new approaches to quantum machine learning that work within quantum constraints while leveraging quantum advantages for computational speedups. The financial applications of quantum computing extend far beyond cryptographic security to encompass optimization problems that could transform global markets. Portfolio optimization, risk assessment, and algorithmic trading all involve mathematical challenges that could benefit from quantum acceleration. High-frequency trading firms already invest billions of dollars in computational infrastructure to achieve microsecond advantages in market timing. Quantum trading algorithms could provide even more dramatic performance improvements while enabling new approaches to market analysis. Monte Carlo simulations used throughout the financial industry for risk assessment and derivative pricing require enormous computational resources for accurate results. These simulations often run for hours or days on powerful classical computers to achieve statistical precision needed for financial decision-making. Quantum algorithms could potentially achieve similar accuracy with exponentially fewer computational steps, enabling real-time financial modeling that adapts to market conditions as they develop. Options pricing models depend on solving partial differential equations that describe how financial derivatives respond to changes in underlying asset prices, volatility, and time. Classical numerical methods for solving these equations require significant computational resources that limit the complexity of financial models. Quantum differential equation solvers could enable more sophisticated financial models while reducing computational costs. Credit risk assessment involves analyzing correlations between borrowers, economic conditions, and market factors that create combinatorial optimization problems. Classical risk models must make approximations that introduce uncertainty into lending decisions. Quantum optimization could potentially identify risk patterns that classical analysis methods cannot detect while providing more accurate assessments of portfolio-level credit exposure. The logistics industry faces optimization challenges perfectly suited to quantum algorithms that can explore multiple solution pathways simultaneously. Supply chain management, transportation routing, and inventory optimization all involve combinatorial problems where the number of possible solutions grows exponentially with problem complexity. Classical optimization algorithms must explore solution spaces sequentially, often settling for approximate answers because finding optimal solutions would require computational resources that don't exist. Global shipping networks involve coordinating thousands of vessels, ports, and cargo loads while accounting for weather patterns, fuel costs, and delivery schedules. Quantum logistics algorithms could optimize shipping routes and schedules in real time, adapting to disruptions while minimizing costs and environmental impact. The ability to solve these optimization problems efficiently could reduce global shipping costs while improving delivery reliability. Urban traffic management presents similar optimization challenges where quantum algorithms could coordinate traffic signals, routing systems, and public transportation networks to minimize congestion while reducing emissions. Smart city applications of quantum optimization could integrate transportation, energy, and communications infrastructure to maximize efficiency while improving quality of life for urban populations. The aerospace industry presents applications where quantum simulation could revolutionize aircraft and spacecraft design processes. Fluid dynamics simulations required for aerodynamic optimization push classical computers to their computational limits while still requiring extensive wind tunnel testing and prototype development. Quantum fluid dynamics simulations could potentially model airflow with molecular-level accuracy, revealing optimal designs without physical testing. Spacecraft trajectory planning involves optimization problems that grow exponentially complex as mission duration and complexity increase. Interplanetary missions must account for gravitational assists, orbital mechanics, and fuel constraints while optimizing for multiple objectives including mission duration, scientific return, and cost minimization. Quantum trajectory optimization could find mission profiles that classical methods cannot identify while reducing fuel requirements and mission risks. Satellite constellation management requires coordinating hundreds or thousands of satellites while optimizing coverage, communication links, and collision avoidance. Quantum optimization algorithms could manage these complex systems in real time, adapting to equipment failures and changing requirements while maintaining service quality and safety margins. The chemical industry faces molecular simulation challenges that quantum computers seem uniquely positioned to address. Chemical reactions involve quantum mechanical processes that classical computers can only approximate through simplified models. Quantum chemistry simulations could reveal reaction pathways and catalyst mechanisms with unprecedented accuracy, accelerating the development of new materials, fuels, and pharmaceutical compounds. Catalyst design represents one of the most promising applications for quantum chemistry simulations. Industrial chemical processes rely on catalysts that accelerate reactions while improving selectivity and reducing waste. Understanding how catalysts work requires modeling quantum mechanical interactions between reactant molecules and catalyst surfaces. Quantum simulations could reveal optimal catalyst structures while predicting their performance under various operating conditions. Polymer design involves understanding how molecular chains interact to create materials with specific mechanical, electrical, and thermal properties. Classical simulations can model only the simplest polymer systems accurately, forcing materials scientists to rely on experimental approaches for most polymer development. Quantum simulations could reveal how molecular architecture determines macroscopic material properties, accelerating the development of advanced plastics, composites, and electronic materials. The energy storage industry could benefit enormously from quantum simulations that reveal optimal battery chemistries and energy storage mechanisms. Battery performance depends on complex electrochemical processes that involve quantum mechanical charge transfer, ion diffusion, and electrode interactions. Understanding these processes at the quantum level could guide the development of batteries with higher energy density, faster charging rates, and longer lifespans. Photovoltaic cell efficiency depends on quantum mechanical processes that convert light into electrical current. Quantum simulations of semiconductor materials could reveal new compositions and nanostructures that achieve higher conversion efficiencies while reducing manufacturing costs. The ability to design solar cells computationally could accelerate the development of renewable energy technologies while reducing dependence on fossil fuels. Superconductor research represents another domain where quantum simulation could unlock revolutionary breakthroughs. Room temperature superconductors could transform energy transmission, magnetic levitation systems, and quantum computing hardware. Understanding the quantum mechanical mechanisms that enable superconductivity requires modeling complex many-body interactions that exceed classical computational capabilities. Quantum simulations could reveal the conditions necessary for room temperature superconductivity while guiding experimental efforts to synthesize these materials. The pharmaceutical industry stands to benefit enormously from quantum computing applications that accelerate drug discovery while reducing development costs and improving success rates. Drug molecules interact with biological targets through quantum mechanical processes that classical computers cannot model accurately. Protein folding, enzyme catalysis, and molecular binding all involve quantum effects that determine drug efficacy and side effects. Quantum molecular simulations could predict how potential medications interact with target proteins before synthesizing physical compounds. This capability could transform drug discovery from a process dominated by experimental trial and error into a computational science guided by quantum mechanical principles. The economic implications are staggering, as quantum-guided drug development could reduce timelines from decades to years while dramatically improving success rates. Personalized medicine based on individual genetic variations could benefit from quantum analysis of molecular interactions that determine how patients respond to different treatments. Every person's genetic code contains unique quantum mechanical properties that influence drug metabolism, immune responses, and disease susceptibility. Quantum genetic analysis could enable precision treatments optimized for individual patients based on their molecular quantum signatures. Protein structure prediction represents one of the most computationally intensive problems in biology, requiring understanding of quantum mechanical forces that determine how amino acid chains fold into functional proteins. Classical computers can predict structures for only the smallest proteins accurately, limiting our understanding of biological processes and disease mechanisms. Quantum protein folding simulations could reveal structures for complex proteins while predicting how mutations affect protein function. The quantum revolution in computing, sensing, and communications represents humanity's transition into a new technological era where we can harness fundamental properties of reality itself to solve problems that have constrained civilization throughout history. We are learning to manipulate quantum states with precision that enables capabilities our ancestors would have considered supernatural powers. Yet this quantum transformation also creates vulnerabilities and risks that we're only beginning to understand. The same quantum systems that could revolutionize medicine and clean energy could also enable surveillance capabilities that eliminate privacy while creating weapons that operate according to principles we barely comprehend. The quantum future demands careful consideration of how these technologies should be developed, deployed, and regulated to maximize benefits while minimizing risks. The quantum age is not approaching gradually through incremental technological improvements. It's arriving with exponential acceleration as breakthrough compounds upon breakthrough to create capabilities that seemed impossible just years ago. The organizations, nations, and individuals who understand and adapt to this quantum transformation will shape the future of human civilization. Those who ignore or underestimate the quantum revolution may find themselves as obsolete as mechanical calculators in the digital age. The quantum domain operates according to principles that challenge our most fundamental assumptions about reality, yet mastering these principles provides access to computational, sensing, and communication capabilities that transcend limitations that have constrained human achievement throughout recorded history. We stand at the threshold of the quantum age, equipped with technologies that could solve humanity's greatest challenges while opening pathways to possibilities we cannot yet fully comprehend. The quantum revolution will transform every aspect of human experience, from the medicines that heal us to the materials that enable space exploration, from the algorithms that guide autonomous systems to the sensors that protect our planet's environment. Understanding quantum technologies isn't merely an academic pursuit or professional requirement. It's becoming essential knowledge for anyone who wants to navigate the world that's rapidly emerging around us. The quantum transformation of human society has already begun in laboratories and research facilities around the world. The critical question that remains is whether we'll guide this transformation consciously and responsibly, or whether we'll be swept along by forces we don't understand toward futures we didn't deliberately choose. The quantum age offers unprecedented power to those wise enough to wield it thoughtfully and potentially catastrophic consequences for those who ignore its implications. The future belongs to those who can think quantum, dream quantum, and build quantum solutions to challenges that have plagued humanity since the dawn of civilization. The quantum revolution isn't just changing how we compute, communicate, and sense the world around us. It's fundamentally altering what it means to be human in a universe where the impossible becomes inevitable through the precise manipulation of quantum reality itself. The quantum realm operates according to laws so alien to human experience that our brains literally cannot process quantum reality without mathematical abstractions that reduce infinite possibility spaces into manageable concepts. When you attempt to visualize a qubit existing in superposition, your mind automatically tries to picture it as both 0 and 1 simultaneously, like a coin spinning in the air before landing. But this analogy fails catastrophically because it implies the qubit will eventually collapse into one definitive state, when quantum mechanics reveals something far more disturbing about the nature of reality itself. The mathematical structure underlying quantum superposition exists in complex vector spaces that have no physical analog in our everyday experience. These probability amplitudes live in dimensions that extend beyond the 3 spatial dimensions we can perceive, creating computational possibilities that exist outside the boundaries of classical physics. When quantum engineers manipulate these probability amplitudes, they're literally reshaping reality at its most fundamental level, accessing computational pathways that don't exist anywhere in the classical universe. This manipulation of reality itself has created engineering challenges that push human technology into realms that border on the impossible. Consider the precision required to control quantum states. Engineers must manipulate electromagnetic fields with accuracy measured in parts per million trillion while maintaining environmental stability that exceeds the requirements of the most sensitive scientific instruments ever constructed. A butterfly landing on the roof of a building housing quantum computers could potentially introduce enough vibration to destroy quantum calculations running inside heavily shielded laboratories. The refrigeration systems that cool quantum processors to near absolute zero consume more electricity than entire neighborhoods, while maintaining temperature gradients so precise that they approach fundamental thermodynamic limits. These cryogenic environments create conditions more extreme than the vacuum of interstellar space, yet they must operate reliably for hours or days while preserving quantum coherence across networks of interconnected qubits. The engineering complexity rivals that of particle accelerators or space telescopes. Yet quantum computers must achieve this performance while remaining stable enough for practical computation. Yet when these impossibly demanding conditions are achieved, quantum systems demonstrate behaviors that seem to violate causality itself. Quantum algorithms can solve certain mathematical problems by exploring solution spaces that contain more possibilities than there are atoms in the observable universe. This isn't hyperbole or scientific exaggeration. The computational state space, accessible to a moderately sized quantum computer, literally exceeds the information processing capacity of any conceivable classical system, regardless of how much matter and energy you could dedicate to building it. The implications become even more mind-bending when you consider quantum error correction protocols that can detect and fix errors without ever directly observing the quantum information being protected. These systems use quantum entanglement to create error correction codes that operate by spreading quantum information across multiple physical qubits in patterns so sophisticated that corrupted data can be perfectly reconstructed without destroying the quantum states being preserved. It's like having a secret message that repairs itself automatically even when parts of it are damaged, yet no one ever reads the message to determine what needs fixing. This seemingly impossible error correction capability has enabled quantum systems to cross the threshold into fault-tolerant operation, where adding more qubits actually decreases error rates rather than increasing them. Traditional computing systems become less reliable as they grow larger, because more components mean more opportunities for failures. Quantum error correction creates the opposite behavior, where larger quantum systems become more robust and reliable than smaller ones. This counterintuitive scaling behavior represents a fundamental shift in how we think about building reliable computational systems. The cryptographic implications of this fault-tolerant quantum computing breakthrough have created a security emergency that extends far beyond theoretical concerns about future threats. Current encryption systems protecting everything from personal banking to national security communications could become completely transparent to quantum attacks within the next decade. The mathematical problems that currently require classical computers longer than the age of the universe to solve could be cracked by quantum systems in mere hours. This isn't a gradual degradation of security margins that organizations can address through incremental improvements. Quantum computers represent a binary threat where encryption systems are either completely secure or completely broken with no middle ground. The transition from quantum resistant to quantum vulnerable happens instantaneously once sufficient quantum computing resources become available to potential adversaries. Organizations worldwide are racing to implement post-quantum cryptography before this security cliff arrives, but the timeline remains uncertain and the stakes could not be higher. Meanwhile, the same quantum mechanical principles that threaten classical encryption also enable communication security that approaches theoretical perfection. Quantum key distribution protocols leverage the fundamental measurement properties of quantum mechanics to create communication channels that detect eavesdropping with absolute certainty. Any attempt to intercept quantum-secured communications necessarily disturbs the quantum states carrying the information, immediately alerting legitimate users to security breaches while preventing unauthorized access to encrypted data. These quantum communication systems have already demonstrated intercontinental secure communications using satellite networks and fiber optic infrastructure. The physics of quantum mechanics guarantees that these communication channels provide security that cannot be broken by any future technological advancement, regardless of computational resources available to potential attackers. This represents a fundamentally different category of security that transcends the mathematical complexity underlying classical encryption systems. The development of global quantum internet infrastructure based on these unbreakable communication protocols could revolutionize how sensitive information is transmitted worldwide. Financial transactions, government communications, and corporate data could all benefit from quantum security guarantees that eliminate the constant arms race between encryption developers and cryptographic attackers that has characterized digital security for decades. But building quantum internet infrastructure requires solving engineering challenges that make current internet technology look primitive by comparison. Quantum signals cannot be amplified or copied using traditional methods because quantum mechanics forbids the duplication of unknown quantum states. Instead, quantum networks require quantum repeaters that use teleportation protocols to extend communication range while preserving quantum security properties. These quantum repeaters are more complex than most quantum computers, yet they must operate reliably as network infrastructure components. The sensing applications of quantum technology promise measurement capabilities that approach fundamental physical limits imposed by quantum mechanics itself. Quantum sensors leverage the extreme sensitivity of quantum states to external disturbances, achieving precision levels that reveal phenomena invisible to classical measurement techniques. These sensors can detect gravitational waves, magnetic field variations, and acceleration changes with sensitivity that enables applications ranging from medical diagnostics to earthquake prediction. Quantum gravimeters can measure gravitational anomalies so subtle that they reveal underground structures, mineral deposits, and geological features that traditional surveys cannot detect. These sensors work by measuring how gravitational fields affect the quantum states of trapped atoms, achieving gravitational sensitivity that exceeds classical gravimeters by several orders of magnitude. The applications extend from oil and mineral exploration to archaeological surveys that can locate buried structures without excavation. Medical applications of quantum sensing could revolutionize healthcare by detecting diseases at cellular levels using magnetic signatures produced by biological processes. Quantum magnetometers can detect magnetic fields generated by neural activity, blood flow patterns, and cellular metabolism with sensitivity that reveals physiological information invisible to current medical imaging techniques. These sensors could identify diseases years before symptoms appear, while using magnetic fields too weak to pose any safety concerns. The navigation applications of quantum sensing could provide positioning accuracy that rivals GPS systems without requiring satellite communications. Quantum inertial guidance systems measure acceleration and rotation by monitoring how motion affects quantum states, enabling navigation capabilities that work reliably in GPS-denied environments, including underwater, underground, and space applications. These quantum navigation systems could guide autonomous vehicles, submarines, and spacecraft with precision that exceeds current navigation technologies. Environmental monitoring applications of quantum sensors could detect pollution, climate changes, and ecosystem health indicators with sensitivity that enables intervention before environmental damage becomes irreversible. Quantum chemical sensors can identify trace gases and pollutants at concentrations far below the detection limits of classical analytical instruments. This capability could guide environmental policy decisions while providing early warning systems for industrial accidents and natural disasters that threaten public health and safety. The manufacturing applications of quantum sensing promise quality control capabilities that could eliminate defects while optimizing production processes in real time. Quantum strain sensors can detect mechanical stress, temperature variations, and material composition changes with atomic level resolution. These sensors could monitor manufacturing processes continuously, identifying potential failures before they occur while optimizing production parameters for maximum efficiency and minimum waste. Space exploration missions could benefit enormously from quantum sensing technologies that enable precise navigation and scientific measurement capabilities in extreme environments where classical sensors fail. Quantum sensors could detect gravitational anomalies that reveal the internal structure of planets and asteroids while providing navigation references for precise maneuvering around celestial bodies. These capabilities could guide future missions to mine asteroids, explore planetary surfaces, and establish permanent settlements throughout the solar system. The intersection of quantum computing with artificial intelligence promises hybrid systems that combine quantum parallelism with machine learning capabilities in ways that transcend the limitations of either technology alone. Current neural network training requires enormous computational resources and months of processing time even on specialized hardware designed for machine learning applications. Quantum-enhanced artificial intelligence could potentially accelerate training processes while enabling AI systems that discover patterns completely invisible to classical algorithms. Quantum neural networks could process training data in superposition states, exploring multiple learning pathways simultaneously rather than the sequential optimization methods required by classical machine learning systems. This quantum parallelism could enable artificial intelligence breakthroughs that solve problems remaining intractable for even the most advanced classical neural networks currently under development. The combination of quantum computation with advanced AI could accelerate scientific discovery across disciplines while creating entirely new categories of intelligent systems. Drug discovery represents one of the most promising applications for quantum-enhanced artificial intelligence systems that could model molecular interactions with unprecedented accuracy. current pharmaceutical development requires decades of research and billions of dollars in development costs because classical computers cannot efficiently simulate the quantum mechanical processes that determine how drugs interact with biological targets. Quantum AI systems could potentially predict drug efficacy and side effects computationally before synthesizing physical compounds, transforming pharmaceutical development from experimental trial and error into precision molecular engineering. The financial applications of quantum computing extend far beyond cryptographic security to encompass optimization problems that could transform global markets through more efficient resource allocation and risk management. High-frequency trading algorithms currently invest billions of dollars in computational infrastructure to achieve microsecond advantages in market timing. Quantum trading systems could provide exponentially greater performance improvements while enabling entirely new approaches to market analysis that reveal patterns invisible to classical financial models. Portfolio optimization involves analyzing correlations between thousands of assets while accounting for market volatility, regulatory constraints, and investor objectives. Classical optimization algorithms must make approximations that introduce uncertainty into investment decisions because finding truly optimal portfolios would require computational resources that exceed anything currently available. Quantum optimization could potentially solve these problems exactly while accounting for more variables and constraints than classical methods can handle. Risk assessment models used throughout the financial industry rely on Monte Carlo simulations that require enormous computational resources for statistical accuracy needed in financial decision-making. These simulations often run for hours or days on powerful classical computers to achieve precision requirements for regulatory compliance and risk management. Quantum algorithms could potentially achieve similar statistical accuracy with exponentially fewer computational steps, enabling real-time risk assessment that adapts continuously to changing market conditions. The logistics industry faces optimization challenges perfectly suited to quantum algorithms that can explore multiple solution pathways simultaneously through quantum superposition. Supply chain management involves coordinating thousands of suppliers, manufacturers, and distributors while optimizing for multiple objectives, including cost, delivery time, quality, and environmental impact. Classical optimization algorithms must explore solution spaces sequentially, often settling for approximate solutions because finding optimal configurations would require computational resources that simply don't exist. Global shipping networks present quantum algorithms could coordinate similar optimization challenges where vessels, ports, and cargo loads while accounting for weather patterns, fuel costs, and delivery schedules. Quantum logistics systems could optimize shipping routes and schedules in real time, adapting to disruptions while minimizing costs and environmental impact. The ability to solve these optimization problems efficiently could reduce global shipping costs by trillions of dollars annually while improving delivery reliability and reducing carbon emissions. Urban traffic management represents another domain where quantum optimization could coordinate traffic signals, routing systems, and public transportation networks to minimize congestion while reducing emissions and improving quality of life. Smart city applications of quantum optimization could integrate transportation, energy, and communication infrastructure to maximize efficiency while adapting to changing population patterns and environmental conditions. The aerospace industry presents applications where quantum simulation could revolutionize aircraft and spacecraft design by enabling computational modeling that eliminates the need for expensive physical testing. Fluid dynamics simulations required for aerodynamic optimization currently push classical computers to their computational limits while still requiring extensive wind tunnel testing and prototype development. Quantum fluid dynamics simulations could potentially model airflow with molecular-level accuracy, revealing optimal designs that classical methods cannot identify. Spacecraft mission planning involves trajectory optimization problems that grow exponentially complex as mission duration and objectives increase. Interplanetary missions must account for gravitational assists, orbital mechanics, and fuel constraints, while optimizing for multiple objectives including scientific return, mission duration, and cost minimization. Quantum trajectory optimization could identify mission profiles that classical methods cannot discover while reducing fuel requirements and mission risks. The chemical industry could benefit enormously from quantum simulations that reveal molecular interactions and reaction mechanisms with unprecedented accuracy. Industrial chemical processes rely on catalysts that accelerate reactions while improving selectivity and reducing waste production. Understanding how catalysts work requires modeling quantum mechanical interactions between reactant molecules and catalyst surfaces that exceed the capabilities of classical computational chemistry methods. Quantum chemistry simulations could reveal optimal catalyst structures while predicting their performance under various operating conditions without requiring expensive experimental validation. This capability could accelerate the development of more efficient industrial processes while reducing environmental impact through better catalyst design and process optimization. Materials science represents another frontier where quantum simulation could unlock revolutionary advances in developing materials with properties that exceed current technological capabilities. The electronic and mechanical properties of materials emerge from quantum mechanical interactions between atoms and electrons that create computational problems scaling exponentially with system size. Classical simulations can model only the simplest materials accurately, forcing materials scientists to rely primarily on experimental approaches for materials discovery and optimization. Quantum materials simulations could reveal how atomic arrangements determine macroscopic properties like electrical conductivity, mechanical strength, and thermal stability. This capability could guide the development of revolutionary materials, including room temperature superconductors that could transform energy transmission systems, ultra-lightweight aerospace materials that enable more efficient aircraft and spacecraft, and advanced semiconductor materials that could continue improving electronic device performance. The energy industry faces optimization and simulation challenges where quantum computing could accelerate the transition to sustainable energy systems while improving efficiency throughout energy production, transmission, and storage infrastructure. Power grid management involves coordinating thousands of generators, transmission lines, and consumption centers while accounting for weather patterns, equipment failures, and fluctuating demand. Classical optimization algorithms must make approximations that result in billions of dollars of wasted energy annually due to suboptimal grid operation. Quantum optimization could potentially eliminate this waste while improving grid stability and reducing carbon emissions through more efficient coordination of renewable energy sources. The ability to optimize power grids in real time could enable much higher penetration of variable renewable energy sources like wind and solar while maintaining grid stability and reliability. Energy storage system design involves understanding electrochemical processes that determine battery performance characteristics, including energy density, charging speed, and cycle life. These processes involve quantum mechanical charge transfer and ion diffusion mechanisms that classical simulations cannot model accurately. Quantum electrochemical simulations could guide the development of advanced battery technologies that enable practical electric aviation, long-duration grid storage, and portable electronics with. The quantum dramatically improved performance revolution extends beyond technological advancement to encompass fundamental changes in how we approach scientific research, economic optimization, and global communication systems. We are witnessing the emergence of computational capabilities that could reshape human civilization by solving problems that have constrained technological progress throughout recorded history. Yet this quantum transformation also creates new categories of risk and vulnerability that demand careful consideration of how these technologies should be developed and deployed. The same quantum systems that could revolutionize medicine and clean energy could also enable surveillance capabilities that eliminate privacy while creating asymmetric advantages that destabilize international relations. The quantum future is not approaching gradually through incremental improvements in existing technologies. It is arriving through exponential breakthroughs that compound to create capabilities that seemed impossible just years ago. The individuals, organizations, and nations that understand and adapt to this quantum transformation will shape the trajectory of human civilization for generations to come. The quantum age demands that we think beyond the limitations that have constrained human achievement throughout history, while carefully considering the responsibilities that come with technologies capable of manipulating the fundamental structure of reality itself. We stand at a threshold where science fiction becomes engineering reality, where the impossible becomes inevitable through the precise control of quantum mechanical phenomena. The quantum revolution unfolding around us operates on timescales that make geological epochs seem like brief moments. While you've been reading these words, quantum computers scattered across research facilities worldwide have performed calculations that would require classical systems millions of years to complete. These machines exist in a state of constant computation, exploring mathematical landscapes that classical computers cannot even let alone traverse. Think map about the audacity of what quantum engineers are attempting to achieve. They're building machines that harness particles existing in multiple states simultaneously, controlling them with precision that approaches the fundamental limits of measurement itself, all while maintaining these impossible conditions long enough to extract useful results. It's like trying to conduct a symphony orchestra where every musician is invisible, can play multiple instruments simultaneously, and will vanish entirely if you listen too carefully to their performance. The technical challenges involved would have seemed like pure fantasy just decades ago. Consider the environmental requirements alone. Quantum processors must operate in conditions more extreme than the coldest regions of space while maintaining stability that makes atomic clocks seem crude by comparison. The vibration from a passing truck could destroy calculations that represent months of scientific work. The electromagnetic field generated by your smartphone could introduce enough interference to collapse quantum states that took hours to prepare. Yet despite these seemingly insurmountable obstacles, quantum computers are demonstrating capabilities that hint at their revolutionary potential. Research teams worldwide are achieving quantum breakthroughs at an accelerating pace, with each advancement building upon previous discoveries to create a cascade of technological possibilities that stretch far beyond our current imagination. The most disturbing aspect of this quantum transformation isn't the technology itself, but how it forces us to abandon our most fundamental assumptions about the nature of reality. Quantum mechanics reveals that the universe operates according to principles that violate everything our evolved brains consider logical or reasonable. Particles can exist in multiple locations simultaneously. Information can be transmitted instantaneously across cosmic distances. Measurements can retroactively determine the past states of quantum. These systems aren't philosophical abstractions or theoretical curiosities. They represent the operational principles underlying quantum technologies that are reshaping entire industries right now. The same quantum entanglement that Einstein dismissed as impossible provides the foundation for communication systems that guarantee perfect security. The superposition states that seem to defy logic enable computational capabilities that transcend anything classical physics allows. Understanding quantum computing requires accepting that reality itself operates according to rules that challenge human intuition at the most fundamental level. The particles that make up quantum processors don't just switch between states like classical bits. They exist in probability clouds that span multiple dimensions, processing information through interference patterns that have no analog in everyday experience. The mathematical framework describing these quantum phenomena involves complex number systems that extend beyond the 3 dimensions we can perceive directly. When quantum engineers manipulate probability amplitudes, they're literally reshaping the geometry of possibility space, accessing computational pathways that exist outside the boundaries of classical mathematics. This manipulation of reality's underlying structure has created engineering disciplines that blend cutting-edge physics with precision manufacturing techniques. Quantum device fabrication requires controlling matter at the atomic level while maintaining environmental conditions that approach absolute perfection. Manufacturing tolerances must be measured in fractions of atomic diameters. Temperature stability must exceed the precision of the most sensitive scientific instruments ever constructed. The quality control processes for quantum systems face challenges that don't exist anywhere else in manufacturing. Testing quantum devices requires measuring their properties, destroying without the quantum states being. Statistical evaluate analysis must account for the probabilistic nature of quantum measurements while distinguishing between manufacturing defects and fundamental quantum uncertainty. These manufacturing challenges have spawned entirely new categories of precision engineering that push the boundaries of what's physically achievable on Earth. Quantum fabrication facilities operate under conditions so controlled that they rival the environmental stability of space-based telescopes. Cleanroom requirements exceed those of semiconductor manufacturing by several orders of magnitude. Vibration isolation systems must eliminate mechanical disturbances smaller than the diameter of atomic nuclei. Yet when these impossible conditions are achieved, quantum systems reveal computational possibilities that seem to violate the fundamental limits of information processing. Quantum algorithms can solve certain mathematical problems by exploring solution spaces containing more possibilities than there are atoms in the observable universe. This isn't theoretical speculation or mathematical exaggeration. The computational state space accessible to quantum systems literally exceeds the information processing capacity of any conceivable classical computer. The implications become even more staggering when you consider that quantum computers achieve these capabilities while consuming far less energy than classical supercomputers. Where traditional systems require power plants to drive their computational processes, quantum computers operate using energy levels comparable to household appliances. This efficiency advantage stems from quantum mechanics itself, where information processing occurs through probability amplitude manipulation rather than physical state changes. Quantum error correction represents perhaps the most counterintuitive achievement in the history of computation. These systems can detect and correct errors without ever directly observing the quantum information being protected. The protocols work by spreading quantum data across multiple physical qubits in patterns so sophisticated that corrupted information can be perfectly reconstructed without destroying the quantum states being preserved. The mathematical elegance of quantum error correction codes reveals the deep connections between information theory, geometry, and quantum mechanics. These codes create logical qubits that can survive the destruction of multiple physical components while maintaining quantum coherence across extended periods. The overhead required seems enormous at first glance, with hundreds of physical qubits needed to create single logical qubits. Yet this overhead provides access to computational capabilities that classical systems cannot achieve regardless of how many resources you dedicate to building them. Recent breakthroughs have demonstrated that quantum error correction actually improves as systems grow larger, creating the opposite scaling behavior from classical computers. Traditional systems become less reliable as they increase in complexity because more components create more opportunities for failure. Quantum error correction creates systems that become more robust and reliable as they incorporate additional qubits. This counterintuitive scaling property has profound implications for the future of quantum computing. It suggests that truly large-scale quantum computers will not just be more powerful than current systems, but also more reliable and easier to operate. The quantum computers of the future may require less maintenance and supervision than classical supercomputers, while providing exponentially greater computational capabilities. The software ecosystem surrounding quantum computing is evolving at breakneck speed as researchers develop programming languages, development tools, and algorithmic frameworks specifically designed for quantum systems. Writing quantum code requires fundamentally different approaches from classical programming. Developers must think in terms of probability amplitudes, quantum gates, and entanglement patterns rather than the logical operations familiar from traditional computing. Quantum programming languages like Qiskit, Cirq, and Q-number enable a new generation of quantum software developers to explore computational possibilities that exist nowhere in the classical world. These languages provide abstractions that hide the underlying quantum mechanical complexity while exposing the unique capabilities that quantum systems offer. Learning to program quantum computers requires understanding mathematical concepts that span multiple disciplines, including linear algebra, complex analysis, and quantum mechanics. The debugging process for quantum software presents unique challenges that don't exist in classical programming environments. Quantum states cannot be observed directly without destroying them, making traditional debugging techniques impossible. Instead, quantum programmers must use statistical methods that infer program behavior from measurement outcomes while accounting for the probabilistic nature of quantum computation. Quantum software optimization involves entirely different considerations from classical performance tuning. Instead of minimizing execution time or memory usage, quantum programmers must optimize for coherence time, gate count, and measurement accuracy. The most efficient quantum algorithms often counterintuitively use more resources in ways that improve overall system performance by reducing decoherence effects. The integration of quantum computing with classical systems creates hybrid architectures that leverage the strengths of both computational paradigms. Classical computers excel at logical operations, data storage, and user interfaces, while quantum computers provide advantages for specific mathematical problems involving optimization, simulation, and cryptographic applications. These hybrid systems require sophisticated orchestration software that can coordinate between fundamentally different types of processors while managing the data flow between quantum and classical components. The timing constraints are particularly challenging because quantum operations must complete within coherence time limits, while classical systems handle pre-processing and post-processing tasks. Cloud-based quantum computing platforms are democratizing access to quantum resources by removing the barriers associated with building and maintaining quantum hardware. These platforms provide standardized interfaces that allow researchers and developers worldwide to run quantum algorithms on different hardware architectures while abstracting away the complexity of quantum system operation. The democratization of quantum access is accelerating innovation by enabling researchers who lack access to physical quantum systems to develop and test quantum algorithms. Educational institutions can provide students with hands-on experience using real quantum computers without the enormous capital investment required to build quantum laboratories. Commercial applications of quantum computing are beginning to emerge as systems achieve sufficient scale and reliability for practical problems. Financial institutions are exploring quantum algorithms for portfolio optimization, risk assessment, and fraud detection. Pharmaceutical companies are investigating quantum simulation for drug discovery and molecular modeling. Logistics companies are testing quantum optimization for supply chain management and route planning. These early commercial applications provide crucial feedback that guides the development of future quantum systems. Real-world deployment reveals practical challenges that don't appear in laboratory settings while identifying the specific performance characteristics most important for commercial viability. The quantum workforce of the future will require skills spanning multiple scientific and engineering disciplines. Universities are redesigning curricula to prepare students for careers in quantum technologies, while industry training programs help existing professionals transition into quantum roles. The success of the quantum revolution depends critically on developing human capital with the diverse expertise needed to advance quantum technologies. Educational programs in quantum information science must bridge the gap between theoretical physics and practical engineering while providing hands-on experience with real quantum systems. Students need exposure to quantum mechanics, classical computer science, electrical engineering, and materials science to understand the interdisciplinary nature of quantum technologies. The global competition for quantum talent has intensified as companies and nations recognize the strategic importance of quantum expertise. Recruiting qualified quantum engineers has become a limiting factor in quantum development, with organizations competing aggressively for professionals who understand both the theoretical foundations and practical implementation challenges of quantum systems. International collaboration in quantum research creates opportunities for knowledge sharing while raising concerns about technology transfer and intellectual property protection. The fundamental science underlying quantum technologies benefits from open collaboration, but the strategic applications create incentives for protecting quantum research from potential adversaries. Government investment in quantum research has accelerated dramatically as policymakers recognize the transformative potential of quantum technologies for economic competitiveness and national security. The United States, China, and European Union have launched massive public funding programs, while smaller nations develop specialized quantum expertise in specific application areas. These public investments are accelerating quantum research while creating coordination challenges among different funding agencies and research institutions. The interdisciplinary nature of quantum technologies requires collaboration between physics departments, engineering schools, and computer science programs that traditionally operate independently. Standards development for quantum computing involves establishing common protocols for quantum hardware interfaces, software development tools, and quantum communication networks. These standardization efforts must balance the need for interoperability against the rapid pace of technological evolution that could make standards obsolete before they're widely adopted. The intellectual property landscape surrounding quantum technologies is becoming increasingly complex as companies file patents covering everything from quantum hardware designs to quantum algorithms and error correction protocols. The overlap between academic research and commercial development creates potential conflicts over ownership of fundamental quantum discoveries. Quantum computing represents more than technological advancement. It signals humanity's transition into a new era where we can harness the fundamental properties of reality itself to solve problems that have constrained civilization throughout recorded history. We are learning to manipulate the quantum substrate underlying all physical phenomena, gaining capabilities that our ancestors would have considered indistinguishable from supernatural powers. The quantum transformation extends far beyond computing to encompass sensing, communication, and measurement technologies that approach theoretical limits imposed by quantum mechanics itself. These quantum technologies could revolutionize everything from medical diagnostics to space exploration while creating entirely new industries based on quantum mechanical phenomena. Yet this quantum revolution also creates new vulnerabilities and risks that demand careful consideration of how these technologies should be developed and deployed. The same quantum systems that could solve humanity's greatest challenges could also create new categories of weapons, surveillance systems, and economic disruption that threaten the foundations of democratic society. The timeline for quantum transformation remains uncertain, but the exponential pace of recent breakthroughs suggests that practical quantum advantages could emerge much sooner than most experts predicted. The organizations and nations that understand and adapt to this quantum revolution will shape the future of human civilization. Those who ignore or misunderstand quantum technologies may find themselves as obsolete as manual calculators in the digital age. The quantum age demands that we think beyond the limitations that have constrained human achievement while carefully considering the responsibilities that accompany technologies capable of manipulating reality's fundamental structure. We stand at a threshold where the impossible becomes inevitable through the precise control of quantum mechanical phenomena that govern the deepest levels of physical reality. The quantum future isn't approaching gradually through incremental improvements in existing technologies. It's arriving through exponential breakthroughs that compound to create capabilities exceeding anything previously imagined. The quantum revolution represents humanity's next great leap forward, comparable to the development of language, agriculture, or the Industrial Revolution in its potential to transform every aspect of human civilization. Understanding quantum technologies isn't just an academic pursuit or professional requirement. It's becoming essential knowledge for anyone who wants to comprehend the world rapidly emerging around us. The quantum transformation will touch every industry, every field of science, and every aspect of human experience in ways we're only beginning to understand. The quantum revolution has already begun in research laboratories and technology companies worldwide. The critical question isn't whether this transformation will occur, but how quickly we can adapt to harness its benefits while mitigating its risks. The future belongs to those who can think quantum, build quantum solutions, and navigate the complex landscape of opportunities and challenges that quantum technologies create. The quantum age promises to unleash human potential in ways that seemed impossible just decades ago. We are entering an era where the fundamental limits of computation, communication, and measurement are determined not by engineering constraints, but by the laws of quantum mechanics themselves. This represents the ultimate frontier of technological development, where further progress requires mastering the deepest principles governing physical reality. The journey into the quantum realm challenges everything we thought we knew about the possible and the impossible, revealing a universe far stranger and more malleable than our everyday experience suggests. Quantum computing doesn't just represent faster calculation or better optimization. It opens doorways to computational realms that exist beyond the boundaries of classical physics, where information itself takes on properties that seem to violate the fundamental logic of cause and effect. The quantum computers running in laboratories right now are processing information in ways that should make you question everything you believe about the nature of computation itself. These machines aren't just faster versions of classical computers, they're accessing computational dimensions that exist completely outside the realm of classical physics, manipulating information through mechanisms that operate beyond the boundaries of space and time as we understand them. Consider what happens when quantum engineers create entangled networks spanning hundreds of qubits. They're not just connecting processing units like classical computer architects link CPU cores. They're weaving probability patterns that exist across multiple dimensions simultaneously, creating computational fabrics where information flows through pathways that have no physical analog in our three-dimensional reality. These entangled networks can process data relationships that would require classical computers to explore solution spaces larger than the visible universe. The most mind-bending aspect isn't the speed of these calculations, but the fact that quantum computers can solve problems by eliminating wrong answers without ever computing them. Quantum interference allows these systems to cancel out incorrect solutions while amplifying correct ones through probability wave interactions that occur at scales smaller than atomic nuclei. It's like having a search algorithm that finds the needle in the haystack by making all the hay disappear without ever looking at individual pieces of straw. This quantum elimination process operates through mathematical principles that classical logic cannot accommodate. When a quantum computer runs Grover's search algorithm, it doesn't examine database entries sequentially like classical systems. Instead, it creates superposition states containing all possible answers simultaneously, then uses quantum interference to systematically eliminate incorrect possibilities until only the right answer remains. The system never actually processes the wrong answers, yet somehow knows they're incorrect. The implications stretch far beyond academic computer science into realms that challenge our understanding of information processing itself. Quantum computers can simulate molecular interactions by becoming the molecules they're simulating rather than calculating approximations of molecular behavior. When quantum systems model chemical reactions, they don't compute what molecules might do. They literally recreate the quantum mechanical processes that govern molecular behavior, providing perfect simulations because the simulation and the reality operate according to identical quantum principles. This ability to become what they're simulating has revolutionary implications for materials discovery. Instead of guessing how atoms might arrange themselves in new materials, quantum computers can explore every possible atomic configuration simultaneously through superposition. They can test millions of potential crystal structures in parallel, identifying optimal arrangements that classical simulations would never discover because they lack the computational resources to explore such vast possibility spaces. The pharmaceutical industry is beginning to harness this quantum simulation capability to design drugs that interact with biological targets at the quantum level. Protein folding, enzyme catalysis, and molecular binding all involve quantum mechanical processes that determine how medications work in human bodies. Classical computers can only approximate these quantum biological interactions, but quantum computers can simulate them with perfect fidelity because both the simulation and the biological processes operate through identical quantum mechanisms. Quantum drug design could revolutionize medicine by enabling the creation of medications tailored to individual genetic variations at the quantum level. Every person's DNA contains unique quantum mechanical properties that influence how they respond to different treatments. Quantum genetic analysis could reveal how quantum effects in cellular biochemistry determine drug efficacy and side effects, enabling precision medicine that accounts for quantum biological processes that classical medicine cannot detect. The financial applications of quantum computing extend into territories that redefine what we mean by market analysis and economic modeling. Traditional financial models rely on statistical approximations because classical computers cannot process the enormous number of variables that influence global markets. Quantum systems can analyze market correlations by creating superposition states that contain all possible market scenarios simultaneously, revealing hidden patterns that emerge only when you can examine every possibility at once. High-frequency trading algorithms enhanced with quantum processing could identify arbitrage opportunities by analyzing market inefficiencies across multiple dimensions of trading space. These quantum trading systems wouldn't just react to market movements faster than classical algorithms. They could predict market behavior by exploring all possible trading scenarios simultaneously through quantum superposition, identifying profitable strategies that exist only when you can see the entire market possibility space at once. Risk management models enhanced with quantum computing could assess portfolio vulnerabilities by simulating every possible economic scenario simultaneously. Instead of running Monte Carlo simulations that approximate market behavior through statistical sampling, quantum risk models could explore actual probability distributions that govern financial markets. This quantum risk analysis could reveal catastrophic failure modes that classical models miss because they cannot explore the complete space of possible market outcomes. The logistics and supply chain applications of quantum optimization are beginning to demonstrate advantages that transform how goods move around the planet. Classical routing algorithms must evaluate delivery options sequentially, testing one possible route at a time until they find acceptable solutions. Quantum routing systems can explore every possible delivery sequence simultaneously through superposition, finding optimal solutions that minimize fuel consumption, delivery time, and environmental impact while maximizing customer satisfaction. Global shipping networks enhanced with quantum optimization could coordinate thousands of vessels, ports, and cargo loads in real time while adapting to weather disruptions, fuel price fluctuations, and changing demand patterns. These quantum logistics systems wouldn't just find better shipping routes. They could identify supply chain configurations that don't exist in classical optimization space, revealing distribution strategies that emerge only when you can examine all possible logistical arrangements simultaneously. Urban traffic management systems powered by quantum algorithms could coordinate traffic signals, routing systems, and public transportation networks by creating superposition states that contain every possible traffic flow pattern. Instead of optimizing individual intersections or transit routes, quantum traffic systems could optimize entire transportation networks simultaneously, finding flow patterns that minimize congestion while reducing emissions and improving quality of life for urban populations. The aerospace industry is exploring quantum applications that could revolutionize aircraft design by enabling computational fluid dynamics simulations that model airflow with molecular-level accuracy. Classical aerodynamic simulations must make approximations that require extensive wind tunnel testing and prototype development to validate. Quantum fluid dynamics could simulate every possible airflow pattern around aircraft surfaces simultaneously, revealing optimal wing designs and engine configurations that classical simulations cannot identify. Spacecraft trajectory planning enhanced with quantum optimization could identify mission profiles that classical methods cannot discover. Interplanetary missions involve optimization problems where small changes in trajectory can have enormous impacts on fuel requirements, mission duration, and scientific return. Quantum trajectory optimization could explore every possible flight path simultaneously, finding mission designs that achieve multiple objectives while minimizing risks and costs. Satellite constellation management represents another frontier where quantum optimization could coordinate hundreds of orbiting systems while optimizing coverage patterns, communication links, and collision avoidance protocols. These quantum constellation management systems could adapt to equipment failures and changing requirements while maintaining service quality and safety margins across global satellite networks. The energy sector faces optimization challenges where quantum computing could accelerate the transition to sustainable power systems while improving efficiency throughout energy infrastructure. Smart grid management involves coordinating thousands of generators, transmission lines, and consumption centers while accounting for weather variability, equipment failures, and fluctuating demand patterns. Quantum grid optimization could eliminate the billions of dollars in energy waste that result from suboptimal power system operation. Renewable energy integration presents optimization problems perfectly suited to quantum algorithms that can balance variable generation from wind and solar sources with electrical demand patterns that change continuously. Classical grid management systems must make approximations that result in curtailment of renewable energy when generation exceeds demand. Quantum energy optimization could identify storage and distribution strategies that maximize renewable energy utilization while maintaining grid stability. Battery design enhanced with quantum chemistry simulations could reveal electrochemical processes that determine energy storage performance characteristics, including charging speed, energy density, and cycle life. These quantum electrochemical simulations could guide the development of revolutionary battery technologies that enable practical electric aviation, long-duration grid storage, and portable electronics with dramatically improved performance capabilities. The manufacturing sector is beginning to explore quantum sensing applications that could revolutionize quality control processes by detecting defects at atomic scales. Quantum strain sensors can identify mechanical stress concentrations, temperature variations, and material composition changes with resolution that approaches fundamental physical limits. These sensors could monitor manufacturing processes in real time, identifying potential failures before they occur while optimizing production parameters for maximum efficiency. Additive manufacturing enhanced with quantum process control could optimize 3D printing parameters by analyzing material behavior at the quantum level. The strength and durability of 3D printed components depend on how polymer chains or metal particles bond during the printing process. Quantum materials modeling could reveal optimal printing conditions that maximize component performance while minimizing material waste and production time. Semiconductor fabrication represents another domain where quantum sensing could improve manufacturing yields by detecting contamination and defects that escape classical quality control methods. Quantum chemical sensors can identify trace impurities at concentrations that affect device performance while remaining below the detection limits of traditional analytical instruments. The agricultural industry could benefit from quantum sensing technologies that optimize crop yields while minimizing environmental impact through precision farming techniques guided by quantum soil analysis. Quantum sensors could detect nutrient levels, moisture content, and microbial activity with precision that enables targeted interventions using minimal chemical inputs while maximizing agricultural productivity and sustainability. Climate modeling enhanced with quantum simulation could provide unprecedented accuracy in predicting long-term environmental changes. By modeling atmospheric chemistry at the molecular level, current climate models must make approximations about how trace gases interact with solar radiation and atmospheric particles. Quantum atmospheric simulations could model processes with perfect fidelity, revealing climate feedback mechanisms that classical models cannot capture. Environmental monitoring systems powered by quantum sensors could detect pollution and ecosystem health indicators with sensitivity that enables intervention before environmental damage becomes irreversible. Quantum chemical analysis could identify industrial contamination, agricultural runoff, and atmospheric pollutants at concentrations far below current detection thresholds, providing early warning systems that protect public health and environmental quality. The quantum transformation isn't coming tomorrow or next decade. It's happening right now while you're watching this video. In laboratories scattered across the globe, quantum computers are solving problems that would take classical supercomputers longer than the age of the universe to complete. We've witnessed the birth of technologies that manipulate the fundamental fabric of reality itself, accessing computational dimensions that exist beyond the boundaries of classical physics. The question isn't whether quantum computing will change everything. The question is whether you'll be ready when it does. If this journey through quantum reality has expanded your perspective on what's possible, smash that like button, subscribe for more mind-bending science, and let me know in the comments which quantum application excites you most. The quantum revolution is just beginning, and the future belongs to those who understand it.